Is everybody familiar with the Data Fellows Program? Is anyone here who's not aware of it? Just so any background? You're not aware of it. Okay, so this is a program that NCDS has run for 3 years. It's a solicitation process where we look for early career faculty to submit proposals for doing research in the data science space. We engage mostly our corporate members to serve on a panel to figure out which research areas they're most interested in having us fund. The fellowships are up to $50,000, and they last for a year. I'm looking for David so he can nod that I'm saying all this correctly. And it's an annual event, and we've had 11 fellows so far, and love the idea of supporting early stage faculty. And this is a hot topic, and we want to do all we can to support it. So Stanley Holt, the director of RENCI, is going to give some opening comments before we kick it off.
So I just want to welcome everybody to the 2016 NCDS Data Science Fellows Showcase. A warm welcome, obviously, to our members. And to the two groups of data fellows that are here, the incoming 2016, 2017 data fellows that will be working in the coming year, and then the people who have just finished up the 2015, 2016 cadre of students. So just welcome to everyone. I think it's fantastic. This is his third year. I think Shannon just said effectively the same thing. Third year of this program is designed to give talented early career researchers the opportunity to work on data research that's of interest to our industry partners, largely. Industry and government partners. It's not so much for academics necessarily. And with that in mind, we encourage a very open dialogue between our members and the fellows throughout the afternoon into the evening, where we're going to have a little meet and greet and some drinks downstairs in the atrium. Quite a nice atrium, even if it's rainy outside. It's like we're going through another weather challenge. We'll see how it works out. So be sure you talk amongst one another, and the more impact, the more interchange we have, the more impact that will result. As Shannon said, the data fellows receive up to $50,000 from NCDS to support innovative data science research for one academic year, and this is our passive-a-thon event. The wider range of research that you're going to be seeing today really does make me proud. I think it's a testament to how much is going on in this area, and I'm just really pleased that the NCDS could take this initiative. And certainly we're trying to look for additional funding over the years. We're talking about different sources so we can try to scale this up. Today you're going to learn something about action-centered information retrieval, communicating data visually for decision support, and the many issues related to the personal privacy and the Internet of Things. And that's the first group of presenters, the new fellows, who will share with us their ideas. Our outgoing fellows are going to talk about machine oblivious graph analysis, visual analytics for large-scale temporal events, and the impact of data on and software on science, which is a topic near and dear to my heart. When NCDS launched this program, it was pretty difficult for us to tell what its impact was going to be. But 3 years later, after giving awards to 11 fellows at 5 different member campuses, we think we're really on to something, and now we're talking about joint ventures with other organizations to expand this program to hopefully to the national level, ultimately truly national level. It's one example of how research can translate their work to benefit the private sector and other communities, and in turn it illustrates how industry can have a voice in setting the data science research agenda. I think more than any other, perhaps with one or two rare exceptions, any other field, we think industry has to drive some of the data science agenda for the academic community, because industry is likely to reap the benefit from rapid progress in this area. Obviously, academia will, government will, etc. But I think it's pretty obvious to everybody that data is going to be one of the driving motive forces of the economy in the future. So getting ahead of that now by making sure that your voice is heard in the type of research we do and the type of educational process we offer in higher education, as well down into K-12 ultimately, is very important. I also want to thank the General Administration, specifically Aaron Hopper, the USDA's Research Director, for the generous support for this program. You've been very gracious, thank you. I also want to thank the NCDS members who reviewed the Data Fellows proposal this year and selected the winning proposals. And those folks are Steve Gustafson from GE, Tom Carsey of the Odom Institute, who co-chaired the review committee, as well as Larry Alexander from Drexel, Craig Hill from RTI, Mark Johnson, Steve Edwards from EPA, and Steve Worth from EMC. So thank you all for your time and effort in doing this for the students. For those of you who have yet to be involved in this program, we're always seeking new sponsors and volunteers and people to serve as reviewers and provide ideas and new ways of spreading the word. So don't hesitate to say you'd like to be involved, because we need all the people who can get involved. You can talk to myself, to David, to Shannon, any of the folks that are here. Anybody is going to be willing to help you and try to figure out ways to make good connections. So again, let me just say thank you. Thank you for being here. I hope you enjoy this afternoon. I encourage you to stick around for our cocktail reception at 5:30 down in the atrium. So thank you.
Thanks, Dan. So I talked enough in the first part, so I'm not going to talk much. I'm going to introduce each of the Data Fellows. I do have a timer. The arrangement is 20 minutes of presentation, 10 minutes of questions. I'll leave it up to the presenters on whether or not they want to be interrupted with questions during the 20 minutes. But as our first Data Fellows presenter, it's my pleasure to introduce Marcello Balduccini, who is Assistant Research Professor for the College of Computing Informatics at Drexel University, and he's going to talk about action-centered information retrieval. Thank you, Marcello. Does it work? Yes, it works. All right.
Thank you very much for having me here. It's a pleasure to see old friends and see people whom I didn't know before. My presentation, my project topic is on, it's entitled Action-Centered Information Retrieval. We'll learn about what I mean by that throughout the presentation. First of all, a little bit about me. I was at Drexel. I'm an assistant research professor there. I also have some other academic roles. Before joining Drexel, I was in corporate research for a number of years in upstate New York. My area of expertise, so from a purely technical perspective, it's called knowledge representation and reasoning. Looking at it from a more intuitive perspective, my interest is in how humans acquire knowledge, use knowledge, reason about knowledge. So both the role of knowledge in human reasoning and in understanding the reasoning processes themselves. So anything that's related to data sciences is very close to me, because humans are typically very good with data, very good with knowledge. We can look at things and understand them unless we're overwhelmed, which is another problem. Computers, so-so. And so one of my main goals is to make computers as good as humans at dealing with information, complex information. So the motivation for this project, as we all know, there's a lot of information available to us nowadays. It's online. Some of it, a lot of it is public. Some of it may not be public. It's in private archives, and some people have access to it. So overall, we have a lot of information. We have information overload. The main problem with all of this information is not that it's there. It's how do I get to the information that pertains to me, since there's so much. So as we all know, we have techniques for asking questions to retrieve pieces of information that we're interested in. Unfortunately, nowadays, the way it works is we query a question, we get some results, we sift through them. These results can be viewed as documents pertaining to our question. We sift through them, hope to find our answers there. Sometimes we don't find our answers, and in that case, we have to refine our query and iterate the process. Now, it's not so bad. In general, there's excellent results, excellent interactions, especially on factoids. If you look at Google, and I'll be using Google here just because it's type of information retrieval tool and technique that we all understand, right? We all use it. It's neither the best nor the worst of information retrieval systems, but it's a good, sort of a good average, good baseline that we can all look at. So factoids are great. If you want to know how the U.S. women's soccer team did a couple of nights ago, if you didn't sit through it with my daughter like I had to, you just Google it, and the answer comes out right away at the very top of the results page. In fact, it even has an ad hoc interface for presenting information. So Google is certainly, definitely aware of what we're talking about, so you understand it. It's a lot more difficult, unfortunately, when we're dealing with more complex information sources and queries. In particular, there's lots of medical records, lots of documents describing historical events or business transactions, and their outcomes, right? So maybe the documents describe the events, but maybe we are interested in effects, right? So our question is, did this business fail, or is this business now bankrupt? And to answer the question, we need to find the document that actually describes the story of the business. And maybe it doesn't even say that it's bankrupt now. It only discusses the final events in the business's history. So when we're looking at this kind of information and this kind of queries, that's when we go back to the iterative process of asking the query, getting an answer, sifting through the results, and iterating. It's a very frustrating, at least for me, process, and I end up doing it very frequently for all sorts of queries. So the question is, can we do better than that? If I had a human instead of a Google search engine, I'm sure the human could do better than that. But how do we achieve that type of performance in understanding the information and answering my questions? So just so that we are all on the same page, let's look at an example. It's a simple example, but let's look at an example of what I'm talking about. So Drexel, as you may know or may not know, has an urban campus. So the university area is an integral part of the urban tissue. We don't really have a separate campus, standalone campus. And there's a building in this area called the Rush Building. It's actually a very nice historical building. Suppose we wanted to ask a question about this historical building and say, did Drexel own the Rush Building in 1972? The number is pretty much picked at random, except I wanted to get a certain kind of results. So if we ask Google these results, a couple of days ago, Google gave what you can see here on the slide. So first of all, notice in boldface, Google shows us the reasons for the selection of those results, essentially the matches with the keywords from our query. So the first entry is a good one, at least on the surface. But now if you look at it in more details, you're going to see that it's returned only because it mentions Rush Building and Drexel. In fact, if you look at it this way, the main match is Drexel and Rush Building are together in the URL of the web page that's being returned. I mean, it's okay, but it completely ignores the notion of ownership and 1972. In fact, this could as well be the URL of the Drexel library that has possibly an archive on the Rush Building, because the Rush Building is such an interesting building. But it doesn't really mean that Drexel ever owns, even now, the building. If a user reads the rest of the text, it sort of emerges that Drexel owns the building. CCI is part of Drexel and it's housed in the building, so it sort of suggests it, but Google has no idea. So for all intents and purposes, this is irrelevant, and most of all, it's irrelevant to my question. If you look at this page, it doesn't really talk about the history of the building or when Drexel acquired it. I believe it doesn't say it at all. The second entry is even more interesting. So it is a match because it mentions the Rush building, it mentions 1972 and Drexel. Perfect. Doesn't say ownership directly. Unfortunately, if you look at it more carefully, you see that the match with 1972 and Drexel has nothing to do with the Rush building. In fact, it's talking about a rowing event. So completely off track. And in spite of the title, Timeline of Drexel History, it doesn't really contain anything pertaining to the Rush building. In fact, the match for building is for main building, not Rush building. It's a different building. The bottom two entries of these top five, so top five is pretty good, right? And the bottom two ones, they are completely off track. Nothing to do with my query. Now, what I'm focusing on is the third one. It's actually a good one. It is about the Rush building. There's a decent amount of matching. It talks about a building, mentions Rush building, Drexel, and then mentions did, the word did. Not a great match, and kind of troublesome to see that it's used as a reason for returning the answer. If you read this webpage, it actually gives you the information you were looking for. So I've highlighted it here. Somewhere in the middle of the page, it says in 1971, Drexel purchased the building, and it's referring to the Rush building. So that's it, right? Well, the troublesome thing is this sentence is not returned as part of the match. Basically, Google completely missed that the source talks about in 1961 Drexel buying the building. It has no idea. It's returning it because of the things that you see here, not because of the good reason. So it's returning it for the bad reasons, not for the good reasons. So how do we improve on this? Before we look into ideas on improving it, let's look at the technical, somewhat more technical aspects of what's going on under the hood. So the task that Google is performing and that we all aim for is the task of information retrieval. Okay, so we can describe it as a task in which you're given information sources, documents, and the user provides some kind of query. Typically, it's a phrase, of course. As we know, you can go with graphical queries and so on. But let's say that it's a phrase. The task is that of retrieving the most relevant, the documents that are most relevant to the query. And the key is, of course, to define what most relevant means. Once you do that, you're off the hook. Now, in traditional information retrieval, most relevant is defined as follows. From a procedural perspective, you take your documents, you separate them in keywords and terms, and you do the same thing with your query. And then you measure, so relevance now is going to be measured in terms of overlap of terms between the document, each source, and your query. That's what we saw Google do by putting things in boldface. That's the overlap. Like I said, Google is not, neither the best nor the worst. The most advanced information retrieval techniques use synonyms. Kind of obviously, Google does plenty of use of synonyms. They use grammatical structures, compare grammatical structures, and use them to better understand what we're asking for and what the queries say. Now, one interesting thing, it's sort of an aside, is Google doesn't really use grammatical structures. Definitely didn't use them in selecting. I think this was the second entry from the previous slide. As you can see here in my query, I said, did Drexel own the Rush building in 1972? So Rush building and 1972 are in a pretty strong grammatical relationship. In the result that Google returned as second result, we indeed have 1972 and Rush building, but they are separated, as you can see from the ellipses here, by a pretty long piece of text. And grammatically speaking, they're completely separated in a relationship that's completely different from what we have in my query. There's good reasons to use grammatical structures, right, because they extract more information from what we are saying and the sources are saying. But in this case, it shows that it's also a good idea sometimes not to use or not to consider grammatical structures too strictly, because source documents are typically have more space to talk about a subject. Whereas in a query, I'm bound to try and squeeze all the key information in a single sentence or single phrase. So the grammatical structure of the query, in many cases, will be quite different from the grammatical structure of the source and the key information in the source. So this is traditional IR. This, as we have seen, if we follow the example based on Google, doesn't really help us too much when we're talking about sequences of events that are described in sources and about which I'm asking queries. Recently, a couple of years ago, some researchers noticed that, and they proposed a different definition of the notion of most relevant. So they focused specifically on events, and they said, suppose we have sources and queries that both describe events, both mention events, sequences of events to be precise. Well, then what we can do is we can extract references to these events using some kind of natural language processing techniques from sources and query. We can also extract the relationship between these events, which one precedes which one, before, after, overlaps, and so on. Well, once we have that, we can build graphs. We can construct a graph for the query and a graph for each document or source. And at that point, relevance can be based on overlap, indeed overlap, but overlap between the two graphs. Okay. So that helps a lot because it abstracts up from the level of how things are written to the relationship that exists between the events. And they have run experiments that demonstrated that this technique indeed improves the accuracy of information retrieval over traditional IR. Of course, in these cases, event-based. In fact, we call it event-centered IR. So event-based, event-related information. So that's an improvement. It doesn't really, it doesn't completely help us because there are cases in practice in which the source may be about events, but maybe the query is about the state of the world after, before, or during those events. Okay. Examples, some very simple examples of this specific kind is who owns that building? That's about the state of the world, but that all depends on the various business transactions that resulted in the current state of the world. So how do we extend these techniques to answer this kind of queries, possibly more sophisticated? So my goal is, in fact, to create extended IR techniques, or to study, I should say, extended IR techniques that allows us to deal with sources that mention events. Medical records, business transactions, computer logs, cybersecurity, or reports. And queries that are indeed about events, but also together or in alternative include questions about the state of the world before, during, or after the events. The example that I gave you earlier about the Rush building, that's a typical example. Ownership is state of the world, but it's kind of unusual to find documents that are going to talk specifically about that time frame. Right? Typically, you're going to have to look at some sequence of events and then figure out what the state of the world was at that time. So how is it that I envision a system based on extended information retrieval techniques to answer? How is it going to answer a question like this? Well, we had that piece of text that I showed you earlier that says in 1961 Drexel purchased the building. Well, the intuition is from the purchase event, we can use world knowledge to conclude that in the resulting state of the world, Drexel owned the building, right, owned Rush, and that's in 1961, right after the purchase event occurred. Now, also, again, using world knowledge, we know that ownership persists normally. So we can build a mental model, mental picture of 1962 in which Drexel still owns the building due to the fact that we have a mental model in which Drexel owned the building in 1961, just from persistence. And this, at this point, is about the state of the world. So the sentence Drexel owns Rush in 1972, that's about the state of the world, and it can be matched directly with our query. So we can conclude that the piece of information from which we extracted all of this is relevant to the query. Incidentally, I should mention that world knowledge is important to this. Right? So I used it in 2 spots in this very simple derivation. I'm not going to go into it. I don't have the time for that. But the idea I'm proposing, the idea I'm studying, heavily leverages the availability of world knowledge, which is a challenge in itself, but we assume that that's somehow available. Now, looking at things into a little more details, what's the approach? Okay, so let's look at the approach. That's actually the key slide to me. There's how do we do that? There's artificial intelligence techniques that have been developed in a completely different context from information retrieval. In which a type of graph called transition diagram has been defined. Transition diagrams are similar to the graphs I showed you earlier, but they allow us to represent both the events that occur and their effects. And on top of that, reasoning algorithms. Algorithms have been defined that allow us to reason about these diagrams so that we can reason about events, their effects, the direct effects of events, as well as indirect effects, side effects, and possibly hidden effects. So the idea is that we can use these transition diagrams. So we can represent query and source as transition diagrams, similarly to what was done in 2014. Take a source that says John bought that house. Well, that may be translated, that may give us a transition diagram of this kind where the arrow, the arc, says that the event of buying the house occurred. It gave us a successor state in which John owns the house. And, based only on explicit information from the source, we don't really know what was true initially. Now, of course, we don't like not to know things about our sequence of events and the states of the world, but we can use reasoning for that. We all know that if we buy an object, we couldn't own it in the state before that, right? So we can apply reasoning, well-known reasoning techniques, in fact, to conclude that in the state preceding the buying action, John did not own the house. Now, suppose you're given a question that says, did John initially own the house? Well, that can also be represented as a transition diagram, a very simple one, in fact. And now we can match the transition diagrams, and we can do so not based on events, but based on the states. So we can compare this state with the initial state in the transition diagram from the source. And we're going to have a match, a special match in this case, that says that it tells us, well, he didn't own the house, but it's still relevant information either way, right? Okay, I'm going to skip the challenges, but there's some important, obvious challenges. Being able to infer information about the state of the world that is not, or events too, that is not explicitly stated, that's a challenge, but also uncertainty. We don't know a lot of things. We don't have enough knowledge. So the IR techniques need to be able to deal with uncertainty in a reasonable way, as I always go back to as humans would do. So we have already started working on this. We started right away, taking advantage of the summer and light teaching load. So these are my final slides. So I'm pretty happy with the progress, I have to say. On the side of the formalization of the approach, formal foundations of the approach, we have focused to begin on sources, as I have described, sequences of events, queries that are about the state of the world after those events. Okay? We have, first of all, analyzed the problem from a purely commonsensical, intuitive point of view to understand what it is that I would expect and when and why. And then we have defined a way of representing the information using these transition diagrams, but we had to expand on the AI techniques quite a bit. And we also defined algorithms that allow us to do the reasoning that we need. We have demonstrated these algorithms and the representation on select cases, just pen and paper. And then once we were happy with this, we also tried an implementation, and we actually were successful. We have a little prototype running. You can see some screenshots here. We tested it on the same case studies that we had defined, and we achieved the results that we were expecting in all of these cases. From a more applied perspective, we have created a couple of tools. One is a natural language processing implementation of natural language processing pipeline that allows us to test different NLP approaches to find the one that's best suited for what we're doing here. On the foundation part, of course, we didn't worry about natural language processing. We assumed that that was done and concentrated on the core of the representation and reasoning, but now we have to worry about natural language processing. And we also created a tool that takes natural language and creates the basis of the reasoning. So these transition diagrams, or to be precise, I should say, paths of the transition diagrams for a smaller subset of cases than the foundation covers. So we're going to have to expand this before we can integrate the two things. We also had a workshop paper accepted, and I'm going to give an invited topic in October, which will include this topic. And we have 2 conference papers submitted. We'll see how it goes. In terms of future work, of course, there's a lot to do, but at least we're in a good spot. Several basic questions need to be addressed. Who, what, when, why. Well, why is really difficult, but who, what, when. Those require a little bit of different handling. Right now, they were essentially yes, no questions, and make no mistake, we're not answering the question. That's really hard. We're not doing question answering, but still, there are different types of questions. Of course, we'll need to expand the template of the queries so that we can deal with states before and after, before and during the events and so on. In tools, we need to integrate everything. We have the bits and pieces so far. And from the point of view of evaluation, that's where we need to do. So we need to identify the right data sets, the right testing strategies, and as I had discussed already in my proposal and later when we had a call after the proposals were evaluated and fellows selected, I have identified NCDS members who are good collaborators, good likely collaborators for this, and in fact I owe them replies as to how we're going to proceed. My main thing was to have something to, concrete that we could start from, because I had to make sure I clarified my ideas. That's all I have.
Thank you.
Marcello, questions?
So, I've got a few. Let's see, which one do I want to start with? Maybe I'll start with this. And so I think it relates to your test data and how it's structured. So you kind of have 2 things that go into being able to answer these questions. One is if you're having to go into just a ball of text, the data mining aspects of how do I pull out and parse this information. You talked about your natural language processing, and versus if it's slightly better structured, then you kind of gain some there. So just in general, where do you think the biggest bang is? Like, do you think we're getting to a point where the mining will be sufficient and the need for structure is lessening? Or do you think there's really a need for both at this point? Be able to answer the kinds of questions you're trying to do.
Well, so the natural language processing aspect is still very tricky, especially the moment you start talking about sequences of something, especially of events. It is very easy to get things wrong in doing the processing. And that's why we split it this way. We said, let's assume that the natural language processing is done. We have the answer, well, we still don't. We have to understand the reasoning. And separately, we're addressing natural language processing. I think there is good value in proceeding this way, because there is good value even if we are just able to get the reasoning done as I have described it, and to apply it to more structured knowledge. So for example, system logs or even medical records, they're not completely free-form, right? So we may be able to process them in a relatively shallow way without solving natural language processing, and then we can immediately apply this. So I think there's a lot of value in even just that side of things. It doesn't require getting natural language processing to a great level. But I also think, however, that because we're focusing on situations in which I have uncertainty about how the events really occurred and their effects, we may be able, that's really my dream, we may be able to compensate for lower quality of natural language processing. Okay? So maybe we don't need to be that great at natural language processing, and if that's the case, then of course there's great value in looking at the whole thing, because, I don't know if it's just my experience, but I am constantly frustrated with traditional search engines because of the things I do, either scientifically or even at home. The tools they provide me with, they're not satisfactory. They waste my time. So I think it's a little bit of both ways. More lower hanging fruit, in a sense, is focusing on structured knowledge and reasoning.
One more question. Greg. Sorry, Noel.
No, please.
You go.
No, it's really just a footnote, but the question I was asking myself as I was listening was whether or not there are certain domains or types of queries that lend themselves to the environments of those kinds of events and sequences. And healthcare, obviously, popped up in my mind. And other ones would be sort of diagnostics for complex physical systems, yes, and things like that. Are those the kinds of test sets that you're planning to use?
So at this point, we're thinking of medical records, mm-hmm, historical events, as like the Rush building in 1972. That's an interesting one. It's actually the thing that sparked my interest specifically in this project. It's very hard to say, who owned this at this time in history, or was this person here at this time in history? But if you look at the historical records, if you pay attention to what's happening, you can tell. And cybersecurity, for sure. In fact, cybersecurity would be a case in which you have pretty well standardized ways of representing information. And we've already done work in the past along these lines, but we were not asking queries this sophisticated. It was much, much simpler.
Thank you, Marcello. I appreciate it. So next up is Casey Dietrich, who is a professor in civil construction and environmental engineering at North Carolina State. And as his slides gets pulled up, he'll be talking about mapping and visualization of coastal flood forecasts for decision support. Right up Brian's alley.
Right.
Thank you.
Sorry about that. So I have some animations. That's why I needed to use my own machine. So I'm Casey Dietrich. I'm really excited to be here. share the plan for the research for the next year. I just wanted to mention this project also is going to support a master's student working with me, Nelson Toll, and he's also here today. He's excited to meet everyone and see the work that's happening. So a little bit about me. I'm an assistant professor in the civil engineering department at NC State. I've been there for about 3 years now. I sit in a red brick building on that red brick campus running my computer models. Before that, I was a postdoc at the University of Texas for a couple of years. Before that, I got my PhD at Notre Dame. Before that, I was an undergrad researcher, and I got my master's at the University of Oklahoma. And the neat thing about this is I've been doing the same research all along. So going all the way back to my freshman year at Oklahoma, I was an undergrad researcher running models for coastal flooding and storm surge, and loved it and have continued on all the way through. So I'm flattered that you think I'm an early career researcher, because I've been doing this for 17 years now, even though my hairline would say otherwise. So that's the reason for this slide. It's not to brag about all the great college football games that I've been to, especially not this year. But especially when I started my PhD in August 2005, I was already doing this work. I've been doing this for 6 years at the University of Oklahoma, and so I was well prepared to contribute, especially because August 2005 was when Katrina went through the Gulf and caused a lot of flooding and damage in New Orleans. And I'm sure everyone remembers Katrina. You might also remember Hurricane Rita, which came through a month later, so the second month of my PhD. And there's another storm that's coming through and flooding the southwest part of Louisiana. These are really big storms. I like these animations because they show, even though a lot of the flooding and the devastation was in southern Louisiana and Mississippi, the storm is as big as the Gulf of Mexico almost. It's causing strong winds from Florida through Texas and elevating water levels all along our coast. And so starting with a really big storm, we want to connect the impacts from that really large scale down to the small scales where people live. So this is a picture of southern Louisiana. You can see the Mississippi River coming through here, starting up near Baton Rouge off screen. This is downtown New Orleans. This French Quarter is like right here. The river comes down out through its Mississippi Delta. There's a lot of ways for a hurricane to push water from the ocean all the way into downtown New Orleans. It can come through some of these lakes and come into Lake Pontchartrain on the north side of the city. It can connect up through the marshes just to the south and southeast of the city, or it can come up through some of the man-made canals. So this is a man-made canal that cuts out through the Carnarvon Marsh. Surge can come up there and come all the way into downtown New Orleans. And it did. These are pictures before and after. The top is 5 years before the storm, and the bottom is a full 2 weeks after Katrina came through. And you can see the darker colors in the bottom image are areas where there was still flooding in the neighborhoods on the north side of the city 2 weeks after the storm. There were breaches in some of the drainage canals on the north side of the city. There were other breaches just south of this picture in some of the navigation canals, flooding the lower Ninth Ward and causing devastation that way. And so we want to be able to predict that. We want to be able to come from a large scale, like the entire Gulf of Mexico, consider the entire hurricane, and then connect down to relatively small scales. Some of these navigation canals are, tens of meters wide. The wave setup on the north side of the city in the lake, that's a process that happens over spans of meters in front of those levees that protect the north side of the city. We want to be able to connect across scales that way. And so to give away the ending, we did. This is a simulation from our computer models of the storm surge during Hurricane Katrina. The vectors are the wind speeds, and so you can see the storm coming from south to north. It makes a landfall here along the Mississippi River. It tracks just to the east of the city and then makes another landfall on the Mississippi coast. The colors are the water levels, and so we get a buildup of 4 meters of storm surge along the Mississippi River Delta, and then that storm surge gets pushed to the north and becomes has water levels up to 8.5 meters along the Mississippi coastline. The highest measured high water mark during the storm was 8.8 meters along coast. That's like 27 feet, 28 feet. So a lot of devastation. And you can see the connection across scales here. We're representing the levee protection system around the city and a lot of the small-scale navigation and irrigation canals and all the connectivity up through the marshes as we go through. And so this is part of my PhD work, was working as part of a larger team to help build these models and validate them for Southern Louisiana. And once you have the model, you can do a lot of things. So we've helped the Army Corps evaluate their existing protection system and then design a new surge barrier on the east side of the city. We've worked with FEMA to do some floodplain mapping, and a lot of that in North Carolina has been led out of this building. And you can also do real-time forecasting. And so in the state of North Carolina, we use this mesh. This is an example of one of the models that we use. It was built here by Brian Blanton and others here in RENCI. And it shows how we connect across scales. So we're representing the coastal ocean as thousands or even millions of triangles, each with different sizes. Out in the middle of the Gulf, we have triangles that are really big, or out in the middle of the Atlantic Ocean, triangles that are really big, and then they shrink down in size as you get closer and closer to the coast. And so in these successive images, you can see we're increasing the resolution to represent the floodplains all along the state of North Carolina, to get down into the Pamlico Sound and some of the estuary systems. And then here we're zooming all the way into Roanoke Island. You can see the intense resolution coming through the Oregon Inlet and allowing surge to propagate into the Sound. So millions of finite elements here, triangular elements. At the corners of every element, we are solving equations for how high the water is going to get, how fast it's going to move, what are the wave heights and periods, and a bunch of other information. And we're making forecasts over 3.5 through 5 days during the storm, trying to predict what's going on or what will go on in the future. So these models are run all the time, even when there isn't a storm. Run downstairs on the supercomputers here in this building. The data is archived here at RENCI also. Everything happens automatically. The models sense when there's a new forecast of winds from the National Hurricane Center. Then they initialize all of the model inputs, and they run a simulation through the queue here, and then everything gets post-processed and archived. During a storm, we do this 4 times a day, once for every advisory from the National Hurricane Center. So every 6 hours or so, we're running a simulation and posting results. And each one of these results, we have forecasts of wind speeds, wave heights, periods, surge levels, water velocities, all kinds of information at all millions of those points in the model. So each advisory can be 2 or 3 gigs of data, and we're doing that several times a day. So the question is, how do you go from that high resolution model output to something that can be useful for a decision maker, an end user? And in this project, we're going to focus on the NC Emergency Management Office. So we need to convert this model output into something that's georeferenced, something that's visual, and something that they can connect with other data sets, other sources of information that they're using to make decisions in real time. We do this already. The AdCirc, so our model results are posted online on this website, and you'll notice it has a RENCI URL. And so you can come here and you can see what we're forecasting. This is an example of Hurricane Hermine, which came through a couple weeks ago and ruined my Labor Day. I had reservations in Manio at a bed and breakfast, and I couldn't go. But you can see this was an advisory maybe a day before the storm moved over the Sound, and we're plotting up and visualizing the water levels building up on the backside of the Hatteras Island. We're showing some elevated water levels near Roanoke Island. And you can plot up water levels, wave heights, and everything here. And this is a useful site. This is already, we've done work and we've gotten the emergency managers starting to use this site. And so, for example, during Hurricane Hermine, this was their analysis of our predictions. So this is a comparison between our predicted peak water level in a few of the communities along the coast compared with what was observed by the local emergency managers. And so this was a comparison that was given back to me by the emergency managers. They were really happy with it. They thought this was a pretty good match. At a couple of these places, especially Ocracoke, we're within a couple hundredths of a foot between the prediction and the observed. There's a couple of places where we're off by a little over a foot. That kind of irritates me, but they seem to be happy with this. This is actionable information already for them. The trick is, it's kind of difficult. They have to come into this site separately, pull up some of this information, and this is all that they're using right now are the predicted peak water levels, when there's a lot of other bits of information that we can give them, including duration of flooding or wave height information that they can use to look at impacts on buildings. So the goal in this project is to convert our information and integrate it into this. This is their website, so the Flood Inundation Mapping and Alert Network. And when they say flood here, what they mean so far is riverine flooding. So this is how they visualize and make decisions based on flooding, rainfall-driven flooding, and all the rivers in North Carolina. Each of these little markers is a gauge along a river, and they're color-coded to indicate the risk in that event. This was a screenshot from 2 days ago, so it reflects some of the rain that we've been getting recently. And if you click on one of these orange indicators, it zooms in and you get a picture right at that gauge, right along the river. And there's more than just the river height here. You get the river stage, especially, and you can see it compared to what's a normal or what's a flood stage. But they also have information about the building damages. So they're linking into a completely different data set and saying, 2 days ago when there was this flooding on this creek near Simpson, they were predicting to have 2 buildings flooded and about $2,000 worth of damages to those buildings. So in real time, this is useful to them to see what are the impacts to the coastal infrastructure. And then there are also scenarios. So if you click on this button here, and I'm too chicken to bring up the actual website during my presentation, but if you go to the website and click on the scenario button, it brings up a slider and you can adjust. So what if there was 17-foot stage of water there, and you can see they've mapped out the extents of that flooding for 17-foot stage, and they've adjusted the impacts, and then 68 buildings are going to be flooded and almost $400,000 worth of damages. So this becomes a planning tool for them, both in the short term and in the long term. So looking ahead before a rainy season, trying to understand what the impacts may be. So they've got this well set up for riverine flooding. We've got all the information for coastal flooding, and it's just a matter of connecting it and making it useful for them. So that's the goal: enable informed decision making for coastal communities during storm events. And the objectives are: we need to take our model forecast data and first put it in the correct format for them to use, the correct visual format. But the real research question is how to downscale it. So how to go from our resolution of our triangles and our mesh to the higher resolution topography and bathymetry and other data sets that they're using. And do that in a way that is consistent with the physics of the storm surge problem that we're trying to solve and represent. So, and then assess the implications of that downscaling. So what kind of errors are we introducing by converting between those scales? And then really working with the NCEM so that the end products are going to be used and useful by them. So this project leverages prior support from North Carolina Sea Grant. We had a 2-year project that just finished earlier this year where we were developing new visualization tools for our model output. This was all done in Python and based on older scripts from Rhineland and Riverlit and others. We are expanding them to consider time series information and also to put into Google KML formats. And we did some experimental developmental work the last couple of hurricane seasons. This is all now integrated into the forecast system, so we're generating these new formats, and they're also being included in the RENCI archive of our model output. But right now they're just archived as shape files or Google KML files, and they're just sitting on an archive somewhere. This is an example of a shapefile animation during Hurricane Arthur, so 2 years ago, and it followed a a similar track right over the Sound and caused a lot of flooding on the backside of the Hatteras Island. And so these are our AdCirc model results mapped onto a GIS framework that's still presented on their own with no other data sets linked into them. And this is all available as open source code. We're sharing it on GitHub, and we're trying to get this to be something useful for our larger modeling community. So the downscaling, how can we connect from our model resolution? So maybe the smallest triangles that we use have edges that are 100 meters in length, even in very concentrated regions near coastal communities. How do we get from that resolution to smaller scales? And so this is a schematic that I included in my proposal to NCDS. And so this shows a section of the coast. Maybe the mean sea level is this darker blue line. We've got a raised house. We've got some coastal roadway, and then we've got some other coastal infrastructure back behind. The light blue shows maybe that's the resolution in our model. And so we're predicting the water levels to raise to a certain height. But because we're using 100-meter or 200-meter triangles, we're not able to take that height all the way to the ground level. So maybe there's flooding over here, maybe the road is underwater, or maybe there are impacts on the structure, and we're not able to represent them in our unstructured mesh models. So we want to take those model results and downscale them to a higher resolution with imagery topography, and do it in a way that's still physically consistent. So if this raised roadway is going to block flooding, then maybe we need to extrapolate our flood guidance out to the roadway but not take it any further. Or what's happening if the winds are blowing from right to left in this picture, pushing water away from the roadway. Maybe our model had it correct all along, and we don't want to extrapolate back over here because that would introduce some error into our forecast. So just interpolating, from low res to high res, that's an easy task, but we want to also bring in some higher level downscaling and bring in some of the physics of the problem as we do this. So that's going to be the key research question. So in summary, flooding forecast data will be connected for use by emergency managers. We're going to leverage some existing visualization tools that we've developed. We're going to leverage the forecasting efforts that are ongoing already in the state, and really connect to the emergency managers and put it into a format that they can use, give them another data point to consider during the storm. We have the initial connection to NC emergency management happening right now. I had a meeting with them last week. They're already using our forecast data, but just in a way that is kind of ad hoc and kind of a burden for them right now. And some initial successes during Hurricane Hermine, but I think by next hurricane season, at the end of this project, I'll be able to come back and show some much more significant successes. So downscaling and extrapolation, Nelson's going to have this all figured out by March. And then assess and implement by the next hurricane season. So I'm excited about this project. I think there's a lot of things that we're going to learn as we go along. And I think we can learn a lot from the NCDS partners and the people here at RENCI too. So thanks for having me and take any questions.
So years ago, there was a program called SCOOP. There was the Southern Coastal Ocean Observing Program or something roughly like that. I was just wondering if there was any connection with this. Ludic was part of that SCOOP.
Okay. I'm not familiar with SCOOP, but that's something I
I think the funding just ended for that and sort of marked.
It ended. It was part of SURA,
Yeah.
Southeast University Research Association, and that project essentially ran its course, and we learned a lot. In particular, we learned about what not to do, and some parts of NOAA picked that up and funded the similar extensions to that kind of work through the IUS program. We talk about this forecast system in the context of that IUS program a fair amount, so it's related with some hand wavings.
Other questions?
I've got one. I'm curious about the uncertainty in the forecasts to come out of the simulation. You showed the examples of the 4 or 5 communities that you recently predicted, and some of the stuff I do is in applied statistics, so I'm immediately wondering about
Error bars.
What's the probabilistic estimate around your forecast? Maybe give yourself more credit for being closer than you really were on some of those because maybe the bound is there.
Yeah, and that's something that we're still trying to quantify. During an advisory, we run a kind of best guess simulation. We also kick off a couple of perturbations. So what if the storm was on a slightly different track, or what if it was moving a little faster or slower? So if you go onto that RENCI Sarah site where our model output is being visualized right now, for each storm you might be able to see a couple of scenarios. And that's one way of getting at the uncertainty in the forecast. Really what we would want to be doing is running hundreds of scenarios during each advisory and really getting a handle on the uncertainty. And that's, I've written other proposals to other funding agencies to do that. That's something that we, as a community, are still trying to get a handle on.
So I did not know about, do you say it Feynman?
Feynman, yeah.
I did not know about that. It's a really interesting source. And there's actually major flooding in North Carolina right now.
Yeah.
I was unaware. So one of the things that I think it's been hard for me to wrap my head around is why this type of research isn't better funded. Because when it's needed desperately. And then during the rest of the time, people forget there's hurricanes and flooding events. But it seems to me like between all these pieces of data, you've made vast progress in the last 5 years. I mean, now you can actually go and look, on the coastline and say, is it a good time to go take a vacation?
Yeah.
And why isn't somebody? I don't know who somebody is, but what is the impediment to more rapid progress, to more funding?
That's a question above my pay level, probably. I don't know. I would like to see a higher percentage of my proposals be funded. I think this is one of a critical need, and I think every time there's a big landfalling storm, there's a reminder of that. And I don't know how to answer your question. Yeah, I think at some level somebody's making priorities, and this is being weighed against other also essential research. So this sort of thing where it's kind of leveraging existing tools and existing models and doing something just a little bit new with them, I think that's a really good fit for a program like this, where we have a clearly defined end user in the government, and this is a project that we can accomplish in 1 year of work and really get something useful.
And it would be a very difficult thing to fund from the NSF, for example, because any panel at NSF would look at this and say, you just put stuff together from 2 previous chunks of software, and the computer scientists would just scoff. It's not fun. It's not a new algorithm, so why should we fund it? And it just seems like this kind of terrifically impactful research. You should be applauded. It's the bottom line.
Well, we haven't done anything yet.
You should be applauded when you get it right.
Thank you.
Okay, on that note, thank you, Casey. I'm going to speak more slowly this time, so Shahriar can get set up. This is the third data fellow in this group, and then we will take a break starting at 3:15. And so next up, we have Shahriar Nirjon, who is here at Chapel Hill, a professor in the Department of Computer Science. And he is going to talk about privacy analytics of homegrown IoT data. Welcome, Shahriar. Thank you.
All right, thanks. So, hello everyone. It's a great honor and pleasure to be here at RENCI for the first time. And thanks for the introduction. I go by my last name because that's my nickname.
Okay.
Nirjon.
Nirjon, okay,
that's fine.
Sorry.
So I joined UNC Chapel Hill in Computer Science Department as an assistant professor last year. So
welcome.
I've been working on various different things, including IoT, and this talk is essentially about IoT. Let's get started. So I'm going to talk about privacy of IoT data coming out of our homes. And my talk, at first, I'm going to talk about my own research, like my research interest, what has been done, and what I am doing, and what is my plan, and things like that. Then I'm going to give you an overview of IoT, because there are plenty of definitions of IoT. Everybody has his own definition of IoT. But what is my definition? How do I see IoT? And why it is happening now, and applications of IoT, things like that. What's going on in the IoT domain. Then I'm going to talk about my project overview and give you this motivation of this research and privacy issues, examples. Finally, I'll conclude my talk with the whole research plan. So let's see what I do. My native research area is mobile and network embedded systems. That is something that evolved into IoT essentially. But there are differences. I'll explain those. In my research, essentially there are two boxes, two things I do. The top box is embedded sensor system. So we do build embedded sensor system that is generating data, that is collecting data. And the bottom one is the sensor data processing system where we process the data. And these two boxes are connected via some sort of communication link. Now, in my research, when I'm building something, the front-end embedded sensor system, I do two things. First of all, I look for off-the-shelf sensors. If there is something out there I just can purchase, like smartphones, or Kinect, or pulse oximeter, or digital stethoscope, that I can just purchase, that has APIs that I can use, and I can get data out of it, then I use those. If not, I build my own. Like I have built smart earphones that can detect your heart rate when you are listening to music and plays a song that matches your heart rate. I have built a smart ring that detects your finger gesture that can be used as a keyboard. And this is an antenna, by the way. If you connect this to a laptop or a mobile phone, it can detect GPS signals indoors, and that can be used for indoor navigation, which, by the way, is not possible with regular antennas that you have in your phone. So these are a few of those hardware artifacts that I have built. We're building more things every day. So plenty of new things are coming up. Now, those devices are producing data, and we have to analyze this data so that we can create value out of it, and meaning out of it. So data processing can happen in several different places, like there, in the sensor board itself, or if that is not sufficient, we send some pre-processed or semi-processed data to the phone. Phone does further processing. If that is not sufficient, let's put that into the cloud or some nearby computer or cloud lake, so whatever it is. So there are plenty of different types of challenges in data processing. For example, how much to process inside the phone? How much to process inside the cloud? How much to process on the board? Where is the trade-off? I want to save energy. I want accuracy. I want real-time deadline guarantees, and so on. So these are all the research challenges that I deal with every day. Sensor fusion, how do I collect all these different types of sensor data and combine them? Mobility, these guys are constantly moving. So how do I make sure that data are coming and data flow is not interrupted? Connectivity can go out anytime. So how do I make sure that I'm not losing my data? Energy efficiency, real time, how to partition the data on different components, analyzing the data, and finally the most important and exciting thing that I'm going to talk about today is privacy. So that's in a nutshell what I do, and let's move on to the overview of IoT. So there are many definitions of IoT, and they are different. If you ask 10 people, they will give you 10 different definitions of IoT. If you ask 100 people, there may be 25 different definitions of IoT because there are influences. So this is my definition. I call IoT a fabric that is connecting every object in the world. And the idea is whatever device that you had previously, those are dumb, they do not talk to each other, they were just providing you one service like a watch or a coffee machine or an oven. Now they have Bluetooth connectivity. Now they can run programs, and they want to connect to the internet, and they want to talk to each other. That's the basic idea of IoT. So everything is becoming smart. Everything wants connectivity. Everything wants to send data. Everything wants to be connected to the internet, and we want intelligence in everything. So that's the whole concept of IoT. Now, there are two views or end of IoT. One side, one group of people talk about IoT devices and networks. They mean whatever smart devices they see, like Nest, Ring, or a HoloLens, or smartphone. These are all IoT devices. You can think of like people who are building microprocessors, or like Intel, or working on the device and network side. They kind of like to see this view of IoT. But there are other group of people who think data analytics is the IoT. And all this data that are coming out of these devices, we need to analyze data and make meaning out of it. That's IoT. That's sort of like the view of IBM and other giants. I think both of these definitions are correct, and we need research in both of them, and we need research jointly because we need to understand one part in order to make other part right. So that's the two views of IoT. Now, one question is, many people are skeptical about IoT. They think like sensors were there forever. Sensor network research has been there for like decades. Now, why it is happening now? Why we are excited about this IoT now? Is it a new terminology that we are just using? Actually not. I mean, several things happened in last 5 to 10 years. For example, I have identified 5 things that happened, and that is why IoT is happening now. Number one is sensor technology has advanced to such extent that accelerometers that can measure your acceleration, velocity, and distance, these are the size of the sensor. Look at that. It's shorter than, compared to a quarter, it's like, I don't know, 1/16 or something. This is a pulse sensor, and this is the fingertip of a person. This is a VGA camera, and this is the fingertip of a person. Go to Amazon, you can purchase that for about 15 bucks or so. This is the force sensor. So miniaturization of sensor, this is one tremendous advancement that we had in the past few years. And the second thing that is happening is the miniaturization of computers and microcontrollers. So this is a processor. This is a system on chip. That means it comes with processor, memory, and also some storage. So this is called Intel Joule. This came out about a month ago, and this one costs about $350. And this has 1.7 gigahertz processor. It's a quad-core processor. It has 4 gigabytes of RAM. My own laptop does not have 4 gigabytes of RAM and 1.7 gigahertz of processing speed, and 16 gigabyte of storage. So this is more powerful than most of the computers that's probably you guys are using now. And the third thing is this amazing technology called Bluetooth Low Energy. Now this is not the Bluetooth Classic, by the way. This is Bluetooth Low Energy. Some people call it Bluetooth Smart. Some people call it Bluetooth 4. And the benefit of using Bluetooth Low Energy or Bluetooth 4 or Bluetooth Smart is that these devices last up to 2 years with a single coin cell battery. This is tiny, and you add a small battery, and this can last for 2 years. So now think about this. You can purchase a camera for 15 bucks. You can purchase this one. There are cheaper ones, less powerful ones. You can purchase that. You can connect that to this, and you can create something that monitors somebody's personal life and lasts for years, months, if not years, months, and transmit that wirelessly to somebody else who is listening. So this is creepy. This concerns me, and this could violate everyone's privacy. So that's where my research is. I want to understand how this technology is affecting our life and affecting our privacy. Now, a few things I've seen the device side. I think a few things about the analytics that are happening now. So this is an app. This is called Target Run app. Many of you probably have used. Has anyone used Target Run app here? No. So
My wife has.
good. Okay, yeah, it's possible. And this is the Macy's app. Now, the way these apps work, Targets and Macy's, they attach such small beacon devices. These are sizes. These are the size of a coin or like a small egg, and they attach that to different sections, subsections within the store. And if you are carrying your phone, you go near that section, and an advertisement or a coupon pops up. So it's a way to actually attract more customers to their stores. And Target started that last year. Macy's has started that. So these devices are called nearers. So if you go near them, you get some service. And these are cheap, and these last for several years. Essentially, they are running small microcontrollers and a Bluetooth chip. So for Macy's and stores like Walmart and Targets, these are deployable in large numbers. They can build, enhance their existing applications, provide new services. These are nicely programmable, and these are helpful to provide some services like advertisement coupons. So this is something that's happening now. The name of this technology, sometimes people call it push notifications. So that's number one. A second thing that is happening is predictive maintenance. So I picked two examples. Number one is US Air Force. They're using smart devices to track their trucks that are running all over the country, and they are predicting their failures, where they're going, and they're trying to optimize their operation. And by doing so, they are saving about $1.5 million every year. That may not be too much for them, but it still is something. Another thing is ThyssenKrupp. These guys build elevators. They are also using sensor technologies so that they can monitor how these elevators are performing. If they can predict or detect like whether or not this elevator is going to fail within a few months or it requires some kind of maintenance, these sensors will detect it and they can fix that early. By doing that, they can save a lot of money. Now these are examples of predictive maintenance. This is happening. And final example is what I call the real-time stream analytics. This is the Tesla car. It's a smart car, connected car, and it's monitoring what's behind him, what's in front of him. It has lots of sensors, ultrasounds, cameras, and sensors to detect objects, obstacles, moving cars, and this has to take decision within a very short amount of time. Here we're talking about sub-second amount of time. Everything needs to be detected. A large amount of image has to be processed within milliseconds. So these guys are doing that in that's called real-time programming. I mean, there is a time limit for doing the computation, and it's happening now. So these are all different things that are happening in the IoT data analytics world. Now, my talk today was about privacy, which is the biggest concern in IoT. Like in a future home, I picked this environment. In a future home, there will be many devices in our home, like Nest thermostat or some coffee maker, smart bulbs. They will talk to each other. They will be connected to the internet. They will push data to the internet, and you can imagine there will be hackers who will look into all this data and know about you more and probably sell that data to some other company, or it could be fatal. They can attack you and so on. So this is the biggest concern in IoT at this moment. One of the biggest challenge and the most, I think, talked about problem in IoT now. Now there are two types of vulnerabilities. Number one is that on the device side. That is, these devices that we are using at home, like this is Amazon's Echo device. Who has an Echo device in this room? Only one. Good. This is a good device to have, but be careful because it is
I actually got the tap, so you have to tap it.
Okay, good. So this has another version, tap, that this is Echo. It continuously listens. There is another one, tap, where you have to push a button so that it can listen. There is another one coming in October. That's a smaller one, $50. So that is again continuously listening. So the way these devices work is they're continuously listening. Although they say when you enter a command like Alexa, find me the sushi restaurant. But in order to detect Alexa, it has to listen to the environment all the time, and they're always listening. So it's possible that somebody can hack into this and listen to every conversation that you're having. So what we want is voice commands, okay, let it go into the system, but everything else, we don't want Alexa to hear anything else. Similar example could be in a remote healthcare environment, like say you are monitoring your heartbeats and lung sounds and sending those to your doctor using your mobile phone who is remotely monitoring you. Now, those devices can listen to your heartbeat, lung sound, but I don't want those devices to listen to my speech or sound of appliances, because those are not required for this application to run. So how do I make sure that these sensors listen to what they are supposed to, and they do not listen to what they are not supposed to? So that's the problem I'm working on. That's type 1 vulnerability. And type 2 vulnerability on the data side, which is, let's say, you're wearing this sleep tracker. You use this to monitor your sleep, measure your sleep, and you think like this is 100% secure, and maybe it is 100% secure, very secure, it is encrypted, and their cloud is the best. But how about this? There are smart microwave in your home. There are smart bulb in your home. Now an attacker, let's say, he can relate, like whenever let's say there are 3 different bulbs, living room, kitchen, and in your bedroom, and one is on sometimes, another one is off sometimes. So by looking at that pattern, and by looking at, let's say, your microwave when it's on and off, he can tell when you had your dinner, now the light is off. From there, he might be able to infer that you are sleeping. So just by securing one particular device at your home is not enough. What I'm saying is there are vulnerabilities because of other unsecured devices in your home. So this is the second form of vulnerability that I'm looking into. So this is a 2-part project. On the first part, I'm looking at acoustic privacy. And the second part, I'm looking at privacy as a generic framework, like analyzing all the data from all the sensors. I separated out acoustic because this is more sophisticated, because it requires more computational and algorithmic challenges there. Here I'm applying a different approach. That's why they're different. I'm going to explain them in a moment. So the part 1, where I'm dealing with acoustic privacy, this is what my plan is. I want to install Amazon Echo in multiple homes, and whatever commands those home people who are living in this home they're entering, I also want to add a custom logger device that we will build in our lab, which will have a similar architecture like Alexa. Alexa has 7 microphones on top of it. There is a reason for that, and we will use an array of microphones similar to Alexa and a processor similar or more powerful than Alexa, so that we can also record, intercept, and log all the commands that Alexa gets, so that we can process them later. Now, what exactly we want to process? Let's say this is a command that the person is giving to Alexa, and if we analyze, there is an algorithm called acoustic source separation. If we run that algorithm, we will be able to separate out all the different types of sources from them. Then we'll see this is an actual command. This is probably an infant crying behind the crying. So if that is the case, an attacker would be able to actually determine whether or not I have an infant kid in my phone. So that's the personal information I don't want. So how do we separate this? How do we hide this? And how do we let Alexa only listen to this and not this? That is one part of my research. So there it involves sound source separation, it involves information leakage detection, and also preventing that. Finally, the generic privacy framework. Here, data is coming from non-acoustic other devices. Let's say we have a thermostat, a smart plug. This is very nice. This is like $30, but you can plug in any device, any appliance there, and it will monitor its state. It will monitor electricity usage and put all the data into the cloud so that you can later analyze how much electricity you're using. But from there, you can actually tell what the person is doing, whether or not he's watching TV or so on. So that's also privacy concerning. So I'm going to install a number of smart plugs in those two homes I'm studying. There will be 2 smart thermostats. There will be smart bands that people will be wearing. There are many other devices that I'm planning and still looking at what are other options there. But the idea is that we'll install some of these smart devices into homes and give those users some of these smart devices and collect those data for 3 months. And those data, some of this data will be on their logged on their phone. Some of this data, because they're not like uniform, they're heterogeneous devices. Some of this data, like Microsoft Band, will sync data to their cloud. These smart plugs, some of this will sync their data to your phone. And for some other data, we might need to build our own smart hub so that we can log this data. So in a nutshell, we will have a number of data sinks that will listen to a number of these smart devices so that we can later do the analysis. And on the analysis side, what we want to do is, let's say we have 3 of different devices. They're generating 3 time series. This is like time axis, and this is like their state, whether or not the TV is on, the microwave is on, or light is on, and so on. So we will do a few things. These are the deliverables. Sort of like, number 1, we want to learn the pattern of usage of a person of a single device or a single device. Then we'll do that for a group of devices, like how do you use multiple devices for a particular activity. And then we'll try to understand the one-to-one correlations of different states of different devices. There will be some devices for which we need to take information from more than one devices. So there is an n-to-1 device state correlations that we want to understand. And we want to also see whether or not, by applying some unsupervised technique, can we detect like what activity the person is doing? Can we tell something like that from all this data? So this is my last slide. So this is a high-level research plan. Like, for example, over the next 12 months, the first quarter, I want to look at all the devices, purchase them, set up the network, select the home, select the participant, and so on. Then there will be data collection in number 2 that will go on for more than 3 months, actually. Then while the data collection is ongoing, we'll also do some research on the audio privacy and IoT stream privacy so that we can build some tools so that as soon as the data is available in quarter 3, we can start the privacy analytics of both of these subtasks. And finally, it will end up with some kind of a paper. So that was it. Yes.
So I'm wondering, I think this is really cool. Would it be possible, do you think, to write a proposal to NSF that at the end of the year you'll have enough data to determine whether or not you can build, I'm not sure what to call it, but a jammer? Because if you look at all this data and you can't detect patterns, maybe you can figure out a way to move the patterns temporarily, not just detract from the actual use. You see what I'm saying?
I see what you're saying. I thought of it, and I wrote a proposal actually, and it was rejected.
Try again.
So let me explain. So when we're talking about acoustic audio, this is in the audible spectrum. So a jammer has to jam the audible spectrum, so it will make noises that we cannot hear. It may be possible to do it this way, like I'm talking now, and because I'm human, my speech is about 4 kilohertz max, so I can install some of the jammers around this room.
I didn't mean an active jammer. I meant, is there a way that you could inject stuff into the stream that you get that gets sent out of your house?
Yeah.
So you either add delays or add false information to confound attackers.
Yeah, that's another way of doing it. And there are existing papers that people have done it. Like, for example, when I was in grad school, we did one project. When you were in home, you were sending a lot of data wirelessly. And there are many sensors. They are firing. And a snooper, an attacker who is outside home, he just uses a spectrum analyzers of some sort. He just listens whether or not there is any wireless communication. Nothing else. He doesn't know which sensor it is. He doesn't know what it is. What he listens to is there is a wireless communication. There has been a wireless communication. He knows the time, by the way, because he has a clock. Now, from there, using unsupervised clustering, you can tell what the activity is doing. So we wrote this paper when we were in grad school, and we have shown how we can fight against that. Simple technique would be delaying the sensor firing, mixing it up, random firing of false sensors. Like an attacker can detect whether or not you are using your mobile phone or your laptop based on how much wireless activity is going on. If it is too much, probably it's laptop. If it is too little, probably it's some sensor. So one way to hide this information is always sending randomly some data. Now there are theoretical paper that proves that no such solution is feasible because the only solution that works is you jam all channels all the time. Any kind of gap in it, an attacker can do some harm to you. So it is an active field of research, and we are looking at it. Thanks for the suggestion. Anyone else? Anyone wants to be my participant?
Brunecco, sure. Okay. Thank you, Nirjon. I appreciate it. Next up, we have Erik Saule, who is at UNC Charlotte in the Department of Computer Science, and he's going to talk about machine oblivious graph analysis.
Thank you very much for the introduction. So before actually jumping into that machine oblivious graph analysis, I want actually to say a little bit about who I am and what my goals are. And you'll realize very quickly that I'm a very different person from most of the people that are here in the room, in the sense that I'm not a data scientist. And I don't want to, I'm going to stress it a bit more than is actually true, but I don't actually care for data science. What I mean by that is that what I
wrong audience.
What I mean by that is that what I care about.
Off the stage.
What I care about is computation and how we make things go fast. And to me, data science, it's an application like an other application could be, and it's a fascinating application, because I feel like there is a lot of need for getting things to compute faster nowadays. And overall, my interests are pretty much always, can always be expressed this way. What I usually do is that I pick a problem that doesn't run fast enough, and I try to use every single trick there is in the book to get those things to run faster. So if that means design better algorithms, then I do algorithms. If that means buy a different kind of hardware, then that's what I'm going to be doing. If that means trying to leverage some more parallelism in the problem, then that's what I'm going to be doing. If that means writing a new software stack from scratch in order to get application experts to be able to express their problem so that all those algorithms and hardware can be developed, then that's what I'm going to do. And what I'm going to do today, and what I want to talk about today, is how I've been looking at that kind of things in order to do graph analysis. But in the general case, I'm interested in any kind of computational problem when you're saying, man, my computer's not fast enough. If you ever think that, come and talk to me, I'll be happy to help. So, more particularly, I want to talk about, I'm interested in this project about graph algorithm. I'm very happy that I came and talked in force, because the first two speakers actually mentioned graphs at some level in their talk. And what I mean by graphs is that graphs are really everywhere, and they're really used at all kind of scale in data science. Here I only use data science application, but actually the second speaker mentioned scientific modeling as one of the potential applications for graph. They can be used for lots of things. So there was a great paper in 2009 that showed that simply by analyzing the graph composed by the road of a city, then you could figure out what was the best location in a city to open your store. And that's a fascinating application. There are lots of other applications. People looked at how we can detect fraud by looking at, for instance, call logs. You can find things like maybe you have some kind of a text, a long text, a scientific article, something like this, and you're trying to see which words are really important words. And by doing some form of graph analysis over the text, you can find which words are important. If you're ever writing a paper and wondering, did I miss any paper that's actually obvious? Then you can actually solve that problem also by doing graph analysis. I looked at that a few years back. It's a simple graph problem. So graphs are important applications, and I feel like pretty much everyone wants at some point in their data analysis to leverage graphs. The thing that's happening is that with those graphs getting bigger and bigger, doing computations over graph became more important, and doing it efficiently became more important. One of the things that people try to do is to try to find which machine actually is going to be the best at solving those graph problems. And it turns out that we are out of luck, because we have 1,000 kind of machines out there, and they are all the best depending on the kind of problem that you have. So to name a few, if you're looking at what you find in your laptops or in servers, you end up having machines that have multi-socket, multi-core CPU systems, where each processor can have a wide range of number of cores in there. You can have machines with 2 cores. 1 core, I don't think you can buy anyone anymore. Maybe in the embedded domain, but besides that they don't even exist anymore. You can buy processors with 12 cores, and each of those cores are composed in thread. They have a weird caching infrastructure. Actually, to be able to leverage the architecture the best, you need to write your code very carefully so that the instruction can be fired in the proper sequence so that you can leverage those parallelism in the machine. You have some of those instructions that can actually work on more than one data element at a time. The size of how much data elements you can use actually depends on the architecture itself. And if you don't do those things, if you just say, well, you know, I'm trusting my code and my code is going to do the right thing, I can tell you it doesn't. I worked with people in geography recently, and they wrote their code in Python because they've been told, oh, Python is great, and it's gigantic, you can do anything you want. I simply took that Python code, I did nothing. I took the code, rewrote it in C, compiled it, it's 60,000 times faster. I am not lying. 60,000 times faster doing nothing. So that's really the kind of improvement you can get just by doing things right, computationally speaking. But actually, the picture gets worse and worse as you keep on going. Intel recently unveiled one of their more recent processors, those Xeon Phi processors. They kind of look like those multi-core CPUs, except they just look like them. They're actually huge versions of those things hybrid and very strange in the sense that they have way more cores. They have even larger capability of executing multiple things at the same time, but the caching hierarchy works completely differently. So if you happen to have written some code that worked on multi-core CPUs, you can recompile it for those new Xeon 5, but you'll get none of the performance. And that's actually the place that you're probably the most comfortable with. If you're trying to use GPUs, they have completely different architectures. They don't even use the same programming language. You need to be careful about exactly what the architecture of the GPU is. Roughly every year and a half, NVIDIA reinvents how GPU works. So you kind of have to adapt your codes as time passes. So it's already a mess and a nightmare when you're looking at a single node. But when you're looking at multiple nodes or at larger scale system, it becomes even worse. Because then you can have clusters of those things that may be heterogeneous or not, with fast or slow network, with accelerators, without accelerators. They can have those SSDs, which have storage devices that provide high I/O speeds. Sometimes you can put them together so that you can get even more bandwidth. And if you don't leverage them correctly, then there is no point in having them. At the same time, that's where the performance is. In the past, we even had weirder architectures like that. XMT architecture that was released by Cray, I think it doesn't exist anymore. I just mention it to explain and to show that you can have really, really weird architectures. So you had that architecture that come with about 8,000 processors, and each of those processors were able to execute hundreds of threads on them, except those cores are actually very slow, and you need to make sure that you can use those millions of threads at a time in order to be able to do any kind of things on it. The good thing about it is that on a single machine, you are having about 128 terabytes of main memory. I'm not talking about disk, I'm talking about main memory. These machines were huge. And once again, if you write your application for one of those XMT machines, it doesn't run anywhere else. And that is the main problem to me. It sounds like whenever you're finding the correct machine, you write your application, you write it for a single machine, then the machine changes, you need to write it again. And if you think that's bad, it gets worse. The reason it gets worse is because algorithms change at the same time. What I mean by the change, over the last few years, we've seen actually 3 major changes in how people think about graph algorithm. People changed a lot how those graphs are actually stored in memory. If you have large graphs, no one wants to store graphs as, oh, here is a string that identifies a node, and here is a set of different strings that identifies the neighbors. People don't do that. They map those vertices into numbers because it makes processing faster. But then how you actually store that mapping makes a huge difference in performance. We can talk about 4 or 5 other times of difference. And even if you're looking at the oldest problem in the graph book, if you're looking at running breadth first search on a graph, it's a problem we've known how to run for 50 years. You know that just 4 years ago, there was a major paper that showed that for the last 50 years we have been doing BFS wrong. There is a different way to do BFS that gets about an improvement about a factor of 10 if the graph you're analyzing is a social network graph. If your graph you're analyzing is a social network and you don't use that direction optimized BFS strange technique from 2012, you're losing a factor of 10. So it means you're buying 10 times more machines than you need. Clearly, people don't do that. People don't want to do that. There are other things that's happening at the asynchronous execution level. I don't want to go into the details. But once again, if you're not doing exactly the right thing, you can lose orders and orders of magnitude. So it's not only that you have to pick the right machine, you also have to choose the algorithm correctly. And if you don't follow up with what is current in algorithm, you're actually losing huge factors of performance. And I actually looked at one problem in particular, the problem of computing betweenness or closeness centrality on a graph. It's a very popular computation that people use in order to find terrorists, or actually the example I gave at the beginning about finding the best location in the city is actually done by running some kind of a centrality computation. And it turns out that there are lots of things you can do on this problem. So the things are algorithmic optimizations. You can do those things like you can find bi-connected components in network, and you can use that to decompose the network recursively. And when you do that, you can get orders of magnitude of improvement. So if you don't do that, once again, you're just throwing computation away. There are other things you can do. For instance, you can do incremental centrality. Whenever your graph changes over time, maybe there is an accident on the road, and so the road is blocked right now, and you want to recompute how those things happen. You don't need to recompute everything. You can just recompute some of those things. But most of the time, people that know about those algorithms are people that actually care about computing centrality correctly. But at the application level, most of the people don't know those things. They just want to compute centrality, and they don't care how you do this. And if they don't follow up with how you compute centrality, you're not going to get the right result. There is even a worse thing that can happen. There is a way to compute centrality where instead of centrality essentially do some kind of BFS iteratively. And it turns out that you don't need to do BFS one by one. You can do them by pack of 1,000. It actually makes the execution much, much faster because it kind of densifies how the computation happens inside your processor. And that has a massive consequence that because you're densifying the computations themselves, it means that all the optimization that you are doing in order to optimize caches or in order to optimize networks become irrelevant. So what I'm trying to say is that it's not just a problem of running one particular graph algorithm. It's not a problem of picking the right hardware. It's a problem of keeping on top of what is the correct hardware I need to run, what is the correct variant of the algorithm I need to run, and how is my graph shaped, and how does the shape of my graph is going to impact my choice of hardware, of algorithm, and of actual implementations. And that's essentially the problem I'm trying to solve. How do we look at all of those things at once and say, this is the actual code I want to run on this particular piece of equipment? That's what I'm trying to solve. Hopefully in a way that the user don't need to worry about it. There has been lots of work in that kind of things to do those graph computations, and most of the time, the answer every time is, oh, there is a new hardware, I'm going to write a new middleware. Oh, there is a new algorithm, I'm going to write a new library. That doesn't scale. People can't keep up with that. So we can't follow those models. That being said, it's actually great to have sources of codes and that are optimized for particular architectures because we want to leverage them. So what I'm actually proposing is to write a new software that will not try to solve all the problem, but that will actually reuse the pieces that already exist and combine them together in a way that whenever you want to run a particular algorithm, it will look at what's available and choose the best way of running those things. The idea is that at the user level, you don't want the user to choose how data is represented. You just want the user to be able to say, all right, I have a graph. How the graph is represented, the user should not have to care. He should just be able to say, oh, I have a graph, it's a directed graph. Maybe he has something else. Maybe he has a mapping of the vertices of that graph to some strings. And these are the concepts that the user has to care about. The great thing about having the user of the system only care about those high-level concepts is that it becomes language independent. You can very easily write wrapper of the system so that the user can write this code in C++ if he likes. If you want to write it in Python, you can do that. If you want to write it in R, you can do that as well. It's just a matter of interfacing. Because at the user level, you're only using high-level concepts. So you don't need to worry too much about the implementation details. That being said, how the data is actually represented in the system is critical. And we want to be able to change under the hood how any of that data is represented. Because if you can't change any of those things, then you might not be able to leverage particular features of your system. So what I'm trying to say is that we need a simple object model, which essentially decouples what the data is for the user to how the data is actually implemented. Fortunately, that's easy. We've been doing object-oriented programming forever, so we know how to do those things. What we need as well is some form of functional abstraction. What we want to be able to say is that we want to be able to have operation exposed to the user that abstract type as a parameter and doesn't specify how any of those operations are done. If you're trying to compute the page rank of a graph, what you care about is computing the page rank of a graph. You don't care that it actually inverses the sparse matrix. It's irrelevant to you. What you care about is, I want the page rank. Do whatever you need to do in order to provide me the page rank. And if the user can express what he needs at that functional high level, then it will leave the implementation the freedom to actually pick the implementation that matches expectations the best. Something else that is great is that if you do this, you can have some form of lazy evaluation. If I know that you're trying to compute PageRank and centrality, maybe instead of computing PageRank first and centrality later, maybe I can merge those two computations together in a way that can provide more performance. And this actually has been done in the past. We have algorithms to do those things. Unfortunately, there are no systems that actually leverage any of those properties. And the good thing about splitting abstractions and implementations is that it allows you to use existing implementation and external tools that are already written. You just need to interface with those things, and you'll be able to use a different library whenever you want to compute on a GPU, and maybe you'll use a different representation. If you want to compute on a cluster, maybe you can use SSDs as well. You just need to figure out what is the existing piece of the software stack that you need to interface with in order to do that, and it can be completely transparent for the user. Finally, in order to complete all this problem, what you need is some form of an execution engine that will look at what the user is trying to do, will figure out what are the available pieces of software, pieces of implementation, what are the available machines to the user, and also how is the graph shaped, and based on that, we'll select which implementation is the one you actually want to run. It looks like a complex problem, but actually we've been doing that in the 70s. That's exactly what your MySQL server is doing when it's doing those execution plans. It has multiple ways of doing those things. It evaluates them and will pick the best one. So I'm not too worried about having that execution engine. The thing that is actually hard, and the thing I want to touch on in that few minutes of my talk, is how do we actually predict how any of those things are going to run? Essentially, you have a bunch of code, you have some hardware you might have benchmarked a little bit in the past, and you need to have an accurate model of how much time it is going to take to run this implementation of PageRank using that GPU on that particular graph. And if you don't have an accurate model of that thing, then any of the thing I mentioned before doesn't matter, because you will not be able to pick the best implementation for the best machine for the job. So you need to have accurate modeling. And that's probably the point where I started to realize that actually the software doesn't matter. What matters is to be able to do those predictions correctly. If we can't do those predictions correctly, there is really nothing the software can help you with. And that's actually the last part of my talk. I just want to give you a very simple idea of why that modeling is complicated. There are some people that try to solve that modeling problem using compilers and essentially annotate the code and let the compiler be able to predict how things are going to run. And these things, they kind of work in the sense that they give you some idea of what's going to happen, but actually graphs are too complicated problems because they're too irregular for compilers to give you good predictions. So what people try to do most of the time is more to have a model where they will know the structure of the graph at some level, and they will model the execution on the particular architecture. I don't want to go through the detail of the model, but that model is essentially saying, well, whenever you're computing PageRank, at the end of the day, your real problem is going to be bandwidth. And so if you can measure exactly how much bandwidth will be used, how much data transfer will be used, then you can have some approximation of what kind of performance you will have. So depending on caching and things like this, different things can happen. So you can get different form of bounds depending if caching happens perfectly, then you get one bound. If caching happens horribly, then you will get another bound. But it gives you some idea of what is going to happen. So once you know how it's going to run on one machine, you can start wondering what is going to happen when we're going to use multiple machines. Because at the end of the day, that's what you care about. You care about knowing, should I use my CPU to do this computation, or should I use the 2 GPUs that are in my machine? In that, you have to make more assumptions, a little bit more. And the main thing that really changes is that you need now to communicate data between your 2 GPUs in order that they can exchange partial version of PageRank. And it's very helpful to actually build those models for a multitude of reasons. First of all, is that they allow you to catch bugs very quickly, because you will run your code and you will see that the performance you obtain doesn't match your model. Most of the time, it means two things. Either your model is wrong and there is something you missed, or your code is wrong and your code doesn't actually do what you think it does. And this happens actually more often than the fact that your model is wrong. Because it turns out your compiler can do crazy things in your back without you actually realizing that the compiler does it. And one of the good things with those models is that it also allows you to identify what are the key parameters in the graph that will predict performance. And actually, in this particular model, the improvement that you will get whenever you go from 1 GPU to 2 GPU is actually linked to the average degree in the graph. So you have a very simple metric that should allow you to tell how much improvement you will have whenever you go from 1 GPU to 2 GPUs. And so that's what we did. Here you'll see different graphs for one particular library, and what happens when the degree change. What we expect are those two continuous lines. We expect that blue continuous line and that blackish continuous line up there. And it turns out that none of the performance that we actually get in practice mapped to our estimation. They kind of map to it in the sense that the trend is correct, but you can see that we are saying that, with a degree of 12, we should always have a speed up which is over 1.2, but actually that's not true. On this particular graph, it gets much lower speed up. And the reason why this is happening is because partitioning of the graph on 2 GPUs never happened correctly. And because it doesn't happen correctly, it actually makes all your assumptions false. And that's essentially what I wanted to tell you about modeling. Modeling is useful. Modeling can be extremely beneficial. It can help you predict what kind of resource you might want to use, what kind of algorithm you want to use. The bad thing is that modeling is insanely hard. I didn't think it was that hard to model those systems. It's actually way harder than I thought when I come in. And right now I'm talking with people from Oak Ridge National Lab that have been doing that kind of performance modeling for a couple of decades now. And they're telling me, yeah, we thought too it was easy. It's really not. And so we are looking at what we can do, how we can instrument compilers, how we can identify key features on the graph to help us figure out which hardware we actually want to run our computations on. So to summarize, essentially what I try to convey in this talk is that graphs are everywhere, and processing them efficiently is a hard software engineering problem, because you have too many algorithms, you have too much hardware, and you have too many kinds of graph for a single person to be able to know what algorithm to use on which machine for that particular graph in particular. We need software to do those things automatically. And my proposal was to build a software to solve that problem. And we make good progress in the sense that we could actually architecture the entire software to be able to do that. We can reuse most of common knowledge in compilers, in object-oriented programming, in algorithms, in execution planning from relational databases. But actually the key piece of the problem that is the hard one, and the one I'm continuing to work on, is how we can model platforms and algorithms in order to be able to predict how much time those things will actually take in practice. And that problem is hard, and that's definitely what I'll be working on in the future. So the software part is actually simple. Just pay a good software engineer and he'll figure it out. We have all the pieces. Predicting runtime, that's the hard one. And on that note, that's pretty much all I had to say.
Thank you. Questions for Erik?
So is there any correspondence? So when you say your modeling is tough, but relatively speaking, is there any way to, like, is the problem of good or better easier than the absolutes of what they are?
Yes, it's easier. It's not easy, but it's easier. It is easier if you're looking at a single kind of algorithm. If you're trying to find, for this particular implementation of PageRank, should I run it on a CPU or on a GPU for this particular graph? You can very easily answer, oh, for this graph, I know CPUs are going to be faster. But if you're trying to look at different algorithms to compute PageRank, and maybe you would run one algorithm specialized for GPUs and one algorithm specialized for CPUs, then that comparison is not easy at all, and you need to actually predict runtime. So hopefully we should be able to predict runtime and with confidence interval on your prediction kind of thing that could help us picking the right hardware. But right now, no, we are not there yet. For one particular algorithm, yes, we can easily say, oh, GPUs are going to be faster on this graph than CPUs. When you try to look at also picking which algorithm to use, then it's an entirely different problem.
And what's your bound? So, within your window of not being able to tell, am I looking at at worst a 10% difference, or can it really be way off?
It can. So what's happening is that because of the irregularities of graphs, we are still not even sure what are the correct features to pick. And you can have things that you think do not matter, but actually matters a lot. If you simply, for instance, step of numbering your vertices from 1 to n, if you number them from n to 1, if you just split the ordering, it would seem like it doesn't change anything. Turned out, for at least 3 of the graphs that I was benchmarking, it makes the entire difference. And the idea is that because they are social network graphs, one of those vertex in one of those graphs has a huge degree. It has a degree of, I think, almost 1 million or something like this. And when you're running this on a GPU, that in the natural ordering of the graph, that vertex is at the end, which causes a huge load imbalance. If for some reason you just flip the graph around, then yeah, okay, you still have that huge vertex, but because it's happening at the beginning of the computation, actually things get filled up correctly. And so even transformation that everyone thinks makes no difference actually matter a lot.
So the prediction effort that you're doing here, is this, I mean, this is out of my area, is this theoretical based on what you know about hardware and systems, or is it you're just running a lot of networks with a lot of algorithms on a lot of machines and running models through the resulting data that categorizes features of the algorithm, features of the hardware, features of the network, turning into kind of a data analysis problem?
So we try to take the data analysis problem path to this. We actually gave the data set to one of my colleagues who's running a machine learning class for graduate students. And they try to do predictions using deep neural network, that kind of things. Turned out that they are not that successful at it. And the main thing that is happening is that they can get trends pretty well. But it turns out that you have those very small effects in graphs that can make the entire difference, the kind of effects I was mentioning, which are usually not well captured by that kind of methods. But I'm actually looking at system modeling right now, and that's what the people at Oak Ridge National Lab are doing. They are looking at measuring latency and of every single operation, measuring fill up of things, and then out of that build a complete model from the ground up.
Thank you, Eric. All right. So next up, we have David Gotts, who is a professor at SILS, the School of Information and Library Science, and he is also the assistant director of the Carolina Health Informatics Program here at Chapel Hill. And he's going to talk about visual analytics for large-scale temporal event data. Thank you, David.
Thank you.
Right.
Let's hope.
All right, very good. Thank you very much. Once again, I'm David Gotts. I'm from UNC Chapel Hill, and I run my little research group, the Visual Analytics and Communication Lab, and I'm going to talk today about kind of one aspect that we do. We talk about a few different things. We study a few different things. But I'm going to talk about my work focused specifically on temporal event data. Now, temporal event data is really common in lots of different areas. What I'm talking about here is a bunch of discrete point events that happen over time that we can organize into a linear sequence, usually organized around kind of one entity. So we have a traveler, for example, who might go in and out of different airports, and those events happen over time. So this is different than continuous data. It's also different than
but it's pretty common to lots of different areas. So if you look at online social media websites, they're constantly tracking what you post and share and people you friend and unfriend. If you look at Amazon, where they're tracking what you click and hover over to see whether you check out of your shopping cart. All that data kind of fits into the same category. In fact, one student that has interned with me when I was back at IBM before I came here is working at Twitter doing this exact kind of analysis. It's also common in things like computer security, where you have a bunch of log files often, where you're capturing a bunch of events over time. So different devices might leave a stream of these point events of different types with a bunch of different attributes. And the data domain that I focus most of my time on is medical data, which also has the same kind of structure. And so for each patient, we have a bunch of encounters with clinicians and hospitals. We have procedures, we have diagnoses, we have medications. And so you can imagine plotting a patient's data over time, just like you had that travel itinerary, where you have, for this patient, these are the things that happen over time. So if we have this kind of data, often what we care about is looking after this particular set of events has happened, what is the outcome, right? So here, if a patient, you can tell I work in medical data. If the traveler, which is me, that is a trip I went on about 1.5 years ago, has to go through that many airports on one trip, they're probably going to end up being a little bit grumpy by the time they get home. But meanwhile, what we really want to do is not just look at one of these sequences, we want to look at a whole collection of them. And so here we have another traveler who has a different outcome. They're much happier. We can look for patterns that are in common across those different groups. So for example, they shared a period of time in Paris where we both went to the same conference. But we have differences in outcomes. So what we'd like to do is start to analyze across this big population of these sequences, what are the things that differ between people with good outcomes and people with bad outcomes, and try and learn from that, that perhaps if you leave Paris and have to hit a whole bunch of cities to get home, you're not going to be as happy. Now, the data that I use, as I mentioned, is coming from the medical domain. And just to give a few examples of typical data sets that I use, one is from the UNC Clinical Data Warehouse, which is the data warehouse that holds all the electronic medical data for UNC healthcare system, which has over 12 hospitals, a whole bunch of outpatient facilities. They have data dating back, in some areas, back to 2004, and they have every single possible medical piece of information you can imagine shoved into this warehouse. So for one patient, if you think back to 2004, assuming they were still in the UNC system, that's a whole bunch of data points with a huge number of different kinds of data. Just diagnosis codes alone, if you're looking at ICD-10, there are 68,000 diagnosis codes. So the number of types of events is really large. The other data set that I work with, and kind of where I get a lot of my practitioners that I work with, is from the UNC Lineberger Cancer Hospital, where they maintain a cancer surveillance system they call ISIS, which is unfortunately named, but it's spelled differently. And basically that system captures 100% sample, or as close as you can get to it, of people who are diagnosed with cancer in the state of North Carolina. So it's a mandatory reporting disease registry. And then they also get data that covers approximately 60% of the state in terms of the healthy population, claims data, and a bunch of other stuff. So overall, it's over 6 million covered lives that they have represented there with a lot of longitudinal data. And they mix in a whole bunch of other things like administrative claims data, economic data, social data from census. And they're kind of there's a whole team of people who do analysis over this data to try and figure out what kinds of interventions work, what kind of screenings work, how medications are effective for different populations, and a whole range of outcomes research. So what my goal is for a lot of the research when I'm looking at this temporal event analysis is to look across these big populations of data sets where we essentially have streams of events that capture the pathway traveled by each of those patients in the medical use case. We'd like to be able to kind of tease apart that data and look in aggregate, what are the key pathways that people follow in time? The same way that if you're driving down the road and we capture sensor data with your GPS, we can figure out where the roads are. Moreover, we'd like to figure out where are there patterns in those roads that people follow in their health record that lead to better or worse outcomes, the same way we can detect traffic and try and route you around traffic. So maybe what we want to do is find out that everyone is traveling down this main road and that's leading to good outcomes, and so there's this weird path over here that people follow where their outcomes are worse, and we'd like to try and redirect those people perhaps into a better path. Or it could be that this is the path that most people are taking, and there's this weird little stretch down here where people are actually getting better outcomes. They're being treated differently. Why are they being treated differently? Well, we have to tease into the data and figure out what is happening there. And perhaps there are other people who are actually going down this path, which we should redirect down this less common path to get better outcomes. So that's the goal of the work that I do. And the kind of to further emphasize that this temporal event data is a little bit different than a lot of data that you shove into machine learning algorithms typically. There's an event coming up at the next IEEE Viz conference in a few weeks, focused specifically on temporal event data. And the challenge here is that it's not easy to map this kind of data into just a nice feature vector representation that you throw into your machine learning algorithms. Because what you're interested in is not just that someone had this diagnosis, but actually that this diagnosis was before this treatment, and it was before this treatment by this much time. You have these temporal relationships, which are complicated. And they're further complicated by the fact that people have different numbers of events and different numbers of data types. So it's not easy to map into this simple matrix form, which we can then compute over. So traditional methods are hard to use to make sense out of this kind of data. And so what I try and do is build tools that help people peer into this data set, where you have millions of patients with tens of thousands of different event types, sometimes hundreds of thousands of event types. ISIS, I asked them to quantify. They guessed about 200,000 different kinds of things that they know about. And that ends up being billions, perhaps more, of individual events, and we want to figure out what patterns within that big event pool lead to good or bad outcomes. So I've worked on a range of different techniques over the years to try and make this data more transparent and more explorable by analysts who are trying to develop hypotheses and do exploratory analysis. And my work in here kind of started back, again, when I was at IBM. I've been at UNC for about 2.5 years. I was in their research division before that. My first kind of step into this, we were looking at heart failure data for a bunch of patients, trying to figure out how they kind of evolve and differences in the patient evolution leading to better or worse outcomes. But what we did is we had all these different event types, and we figured, well, we can't deal with all those different event types, so let's just select the ones that we think are relevant. And so we're going to choose maybe a dozen different kinds of things that we care about. We're then going to aggregate our data around those 12 data types and then come up with this visual representation. There are a bunch of algorithmic things here that we had to solve, but the basic idea is pretty straightforward. Okay? We're going to select a small number of events we care about. Let's say they're specific medications that were ordered, a dozen medications. What we can do is take our data for perhaps millions of patients and aggregate it into a graph-based structure. So we're talking about graphs again. And we can start over on the side over here, where we start with all our patients that have had no medications at all yet. Some people get medication A first, some B first, some C first. After getting medication A, some people go to medication B, other people go to medication C. And so we can kind of capture all the permutations of the events that we care about in these sequences. And if we overlay all of our patients onto this representation, it scales really well, because we're just counting up how many patients are along each path. And we can calculate things like the average outcome, how long it took between one medication to the next one, and the average outcome for people who traveled down one of these paths. So it scales well for the number of patients, but it doesn't scale that well for the number of event types. So we'll get to that in a minute. But to look at this, we just take that graph and map it into a visual representation, where for each node in that graph, I represent with one of these rectangles. This flows from left to right, just like that graph you just looked at, where each layer is the onset of another event, so whether it's a symptom or a medication or something else. And the height of these rectangles corresponds to the number of patients. So this is telling us that twice as many people started with medication A than medication B. That's the kind of data we're looking at. All right, onto that we layer additional information. We add these bars in here where the width corresponds to the amount of time that it took to transition from one to another. So here we're saying people who had medication A first, it took longer for them to change to the next medication than people who started with B first. But people who started with A went to B, and people who started with B went to A, and they're kind of everyone ends up in the same state where they have both medications. Then the last thing we do is we color code them based on the outcome. So if you're not red-green colorblind, you'll see that these folks have better outcome, they're green. These people have red outcome, so they're worse. In a real interactive system, you could change the color palette and be able to see it if you can't. All right, so that's our basic representation. Then we just add these little link lines that allow us to follow and trace through something that looks like that gets created by real data because it's a lot more complicated. And then it becomes harder to lay this stuff out. But what we get is a visualization that looks like this. And I'm not going to walk through this whole video, but I just want to give you a feel for kind of the interactive nature of this. And that here we can see the thickest path through corresponds to actually the clinical guideline for how you treat these heart failure patients. But then we can use this tool to look at variations in medications for heart failure patients, see which ones got better outcomes, and we can find this narrower band at the top that actually seem to do better. We can also go in and change what we mean by outcome. Right? How do we define an outcome? So we can change that, and the visualization will kind of automatically update and redisplay the information. We can focus in on only, for example, medication paths that led to death and start to look at just that subset. All right, so that's kind of the first step, but we had to pre-select just a small number of events. And that means if the information that's important is not in the events you select ahead of time, out of those hundreds of thousands, they're not in the 5 you pick. You're missing it. So there's been some work on simplification, but they had to kind of choose ahead of time. I mean, you had to look ahead of time at this really big, complex mess, and it's too hard to really see what's going on. So the next step that I worked on is embodied in this application I call Decision Flow, where we're now using kind of analytics to help figure out which events are most statistically interesting. But if it's just statistically interesting, sometimes it's not semantically interesting, right? So if you're looking at data about pregnancy, well, women are going to be pregnant, but that's not really that interesting, right? So we want to actually put tools in the hands of domain experts to figure out not just a strong correlation, but that it's actually interesting in terms of their analysis that's been done. So the way we did that is we took our representation, and rather than pre-selecting just a small number of event types that we care about, we're going to take all the events. But we're going to create 2 classes. We're going to create milestone events. Those are things we really care about, and we know we care about. Usually that starts with our query. So we might care about people who have angina first, and then eventually develop heart failure. And those are the people we want to study. So everyone has these milestone events. Then we have a bunch of other intermediate events. That's all the other things that happen in those patients. Then we can take our data structure for all of our patients, make sure they have those milestone events, and then we're going to split our data up into these little subsequences and come up with a data representation where we can group those things together. And we come up with this aggregate structure that looks like this. So everyone, we have a 1-year window of data. Everyone has angina followed by heart failure. And in between, we have a bunch of data about our patients, all the intermediate other things that happen to them, the medications and diagnoses and everything else. And we have some notion about outcome for each of those patients. So from there, we can then start to perform operations. Right? So if we are able to figure out within a particular edge in this representation, if there's one event that seems statistically interesting that the user thinks, I'd like to explore this more, what we can do is take that single edge, find out where that event is that we care about. Maybe it's a particular medication. There are some patients who have that medication, some patients who don't. So we can kind of drop in that event as a new milestone and turn that one edge into 3 more edges, where we have a period of time before the medication, a period of time after it, and then there's a whole other group who didn't have that medication at all. And so now we can do that interactively, recalculate kind of statistics as we go based on the splitting and merging of our data structure, and then map that to a very similar visual representation that we had before. And users can start to explore through the data. So we take the same representation that I just talked about, and we take a visual encoding that looks just like the previous version, except now we have this ability to kind of skip layers, because these are patients who didn't have that event. Right? There's the before, there's after, and then skip. And we just layer on those additional visual encodings. All right, so that turns into an application that looks like this. Does it start? Yeah. Okay. So here is an analysis of, again, related to heart failure, but now we're looking at 500,000 different kinds of events, 3,000 event types. So I'm not filtering down to 6 anymore. It's 3,000 different kinds of things. And what we can start to do is allow the user to look at, this is the start of the time window to when they had a coronary bypass surgery. And we're looking at a visualization of all the intermediate events. This view is a very simple statistical view. It shows us the fraction of patients with good or bad outcomes that have a particular event. So if something's along the diagonal, we have an equal fraction of people in the good and bad population who have it, so it's not statistically interesting. As things get away from the diagonals, there's a stronger correlation with a good or bad outcome. And so users can interactively drag and drop and create new kind of subgroups and just add new types of milestones and do various kinds of flow analysis where they move a mouse over the top and you can see which patients go along which path. And we can do a whole bunch of kind of statistical p-values and everything by calculating here. So we're not confirming stuff, right? We're testing a whole lot of stuff, so that p-value is only worth so much. But at least it says it's interesting, and maybe you want to investigate a little bit further. All right. So that was decision flow and some of the methods there that scale to this high number of events. But as I just mentioned, they're working in this high level, very high dimensional space, and allowing users to quickly subdivide and kind of test stuff has a bunch of challenges of its own. And in particular, if we define some narrow subgroup based on 3 or 4 milestone events that we just kind of dropped into our visualization, what we don't really know is how representative that group is of the larger population. Can we generalize what we've learned from that group to the larger population, or is there something else special about them that we haven't been visualizing? But of course, that's what we really want to do. We don't want to just learn about those 500 patients or 3,000 patients, but we want to learn about the larger population. And so the core fundamental problem here, in many ways, is that people work in low-dimensional representations. So we're querying our data with 3 or 4 inclusion or exclusion criteria. When we work in our visualization, we're specifying 3 or 4 of our inclusion criteria. And in the end up, we're working with a handful of variables, maybe 20 variables. But we have 200,000 variables in the data space. And they're definitely not independent of each other. So when you apply a filter in one variable, you're shifting distributions in all kinds of other ways that you don't really see. And it makes it really hard to understand the value of what you're finding. So that leads to a high risk of selection bias, right? We're selecting a subgroup out of this bigger group, and there are a lot of challenges there. So the work that I spent most of my time on within the NCDS project was to try and get at this problem and to figure out how we can try and not necessarily eliminate it, it's part of this process, but at least make it visible so that people understand it's there and can incorporate that into their interpretation. And so what we did is we built a visualization system not too different from what I just showed, where we capture along the way a representation of the provenance of a user's kind of visual analytic process. So when they get to a particular subset, we've captured all the filters and steps that take them from the beginning to this small subset that they're then analyzing. And it's a kind of, again, another graph-based representation. Users can kind of go down a few steps, back up, and create a new branch as they're exploring through the data. And what we do at each step is we calculate, we kind of characterize the variable distributions for that specific subset of data that they have at each step, and look at the distributions across all the 200,000 variables, or however many we have. And what we want to do then is compare it from where we are currently to where we started as a baseline. And in fact, our system allows you to compare any 2 steps. So we can say, halfway through we had this data set, how does where we are now compare to it? And what we calculate is essentially a distance between distributions. And we do that at the univariate level and then kind of aggregate up to an overall score to show for this step, you've shifted your data set this far from where you started, in addition to seeing all the other statistics. And then we visualize that in the user interface with a kind of a simple set of glyphs across the top that as you explore, we kind of add more boxes and some color coding. So the representation is pretty simple. We have these boxes that correspond to an individual cohort. As you apply new filters, it gets smaller and smaller. This blue part corresponds to the number of patients. In this case, it's a small data set as an example. And then this color-coded bar is the aggregate statistic we computed for the shift in our data sets across all the dimensions. And the dark green tells us that things are great. As we get closer and closer to red, there's a larger and larger shift. And then through the interface, we expose that at the top through this kind of breadcrumb of where you're exploring the data. And then we have a visualization panel that lets you actually dive into that overall statistic to figure out just which dimensions shifted the most. So you can figure out where the bias is being introduced. All right, so as I mentioned, that was the kind of the core element of what we worked on with the NCDS award. And I'm happy to say that we presented that paper at the ACM IUI conference this past spring. And one of the students who helped me the most with this project won the Best Paper Award for our work here. So that was pretty exciting. And we kind of are just scratching the surface here. There's a lot more stuff we can do. To conclude, I just want to highlight kind of our roadmap of where we've been and where we're going. We started with just kind of, let's show the paths. We'll pre-select the number of features. Then we talked about how we can avoid that limitation, where we can actually look at all of the 200,000 variables at the same time. And then we started to work on ways to contextualize the findings that we have into the broader data set so that it's representative. And from there, we have a couple new threads that are going. We're working actively with on an NSF proposal, including a collaborator here at RENCI and someone else in that ISIS center from the School of Public Health to work on these kinds of methods. And we have a whole bunch of aims expanding what you see here. And then also this kind of stuff resonated with a large health IT vendor that has some offices in the area. And so we're kind of in deep discussions now to see whether we can do some industry-sponsored research around that same topic. So all this kind of came from the NCDS award. So for that, I say thank you to NCDS. And that's it.
Excellent. Thank you. Questions? Sure.
David, the visualization you showed were pretty compelling. Is there a tool that anybody can put their data in and create some of the visualization, or would we have to give you the data and you would have to work on it?
There's not like a shrink wrap tool to distribute. I've thought about that. Often most of the data we have is kind of in these proprietary places where it's HIPAA protected and everything. So we build a bunch of one-off data connectors for where the data comes from. But I'd be certainly open to discussing that. If people have that kind of use case in mind, I'd be happy to figure out how we can try and package some of these things. But currently the way it's done is you contact me, and you don't necessarily have to give me the data. That health IT vendor that I talked about isn't going to give me the data, but they're going to give me space on their Microsoft Cloud to install some of the software.
I mean, we've been talking about bringing some visual analytic type tools to exploring the Carolina data warehouse, for example. Mm-hmm. You don't want to be in the position of having to have every faculty member who comes and says, I want to visualize my data. So
absolutely,
having some sort of a package tool, even if it doesn't have all the bells and whistles, but has enough of it that they can see some of what you're able to produce, I think would be quite useful. Because right now, the temporal visual, there is no temporal visualization. It's just, it's essentially required and it's done as part of the ETL, but they really have no way of actually seeing how it's all changing and evolving.
Yeah, so I agree. I mean, the challenge of that is that you have to figure out how I2B2 works or something, and someone has to do that integration, right? And it's valuable, but it's NSF doesn't fund it, right? So that's part of the challenge. So what I work in with is typically with the CDW data, for example, I work with an analyst who exports a bunch of Excel files, and I load in those files, for example.
No, I get what you're doing and why you're doing it. I'm simply saying what would be nice to get to.
Right, agreed.
And you may have just answered this, but the ISIS data, is that in pretty good shape? I mean, is it pretty easy to access, or is it rough?
They have a bunch of data integration challenges and stuff, so their data is rough, but they also spend a lot of time cleaning it. So by the time it gets to me, it's cleaner.
It's good shape.
And typically there's an export that comes that's already cleaned, right? So data cleaning and munging, that's definitely a big problem. Their biggest problem is just figuring out who the same people are, because they're getting data from 5 different insurers, and then they're all the same person in different years, or maybe even the same year, and you have spousal insurance and
trying to link across that to find one person is really hard. Yeah.
I think this is really interesting. The selection bias problem that you're working on, I think, is absolutely important, particularly in a healthcare kind of environment, right, where you get wrong answers. I think it's surprising sometimes to people that to find out that if you select down to a key set of features related to an outcome of interest, that you might actually get less accurate answers by studying the people you care about, those that have a particular disease or whatever.
Right.
So I'm interested in your evaluation of the selection bias. It sounded like you went feature by feature, one distribution at a time, sort of added that up or something like that?
Essentially, yeah, that's right.
So what are the consequences for sort of correlation amongst the feature dimensions? Where you're selection on one, but it's correlated with three other features, lose all three of those distributions.
Yeah, yes, and sometimes that is exactly why there's the selection bias, right? Because that's happening. And so this aggregate feature definitely loses, the aggregate kind of score definitely loses a lot of that information. So a key thing is in our visual representation, we don't throw away the individual values. We actually, there's a separate panel, which it's called the balance panel, we called it, to see how balanced the different dimensions are to the baseline. And there you can really see all the individual values. We have some work going on now where we're looking at clustering those groups to find kind of these groups of variables that move together so that you're not looking at them one at a time, but rather as kind of correlated groups to try and ease the interpretation of how do I understand 200,000 variables that all have a different score. But that aggregate score, while it loses something, is also somewhat important because you can't always look at all of the variables. It takes a lot of time. So it's really just there to say, something's going on, maybe you should take a look. And then you can switch to the other panel where you get a more detailed view.
Okay, thank you, David. So the last one's going to be a challenge because we're doing it via WebEx. It's going to be smooth, piece of cake, all right. Is he on? Can you hear us? Okay. Okay, hopefully you can hear me. So our last data fellow is from Drexel, and he couldn't make it down here as Marcello could. So I'd like to introduce Erjia Yan, who is a professor at the College of Computing Informatics at Drexel. And he's going to talk about assessing the impact of data and software on science using hybrid metrics.
Thank you. Can you hear me?
Yes, thank you.
Okay, excellent. I apologize for not being able to come to North Carolina, but I'm glad that I can talk with you guys virtually through WebEx. So during my last November's Data Byte presentation, I talked a little bit about NCDS supported project on how to identify software packages in food tech scientific applications using a method called bootstrapping. It's highly effective and precision is very high, like 98% above. The recall it's okay, it's about 40% or so. And we identified more than 2,000 software entities in class 1. And those 2,000 software entities covered a wide spectrum of disciplines. And we evaluated those software packages citation impact in terms of number of citations and how many times they have been mentioned in the full text. And so we intended to also use this bootstrapping method to understand how data sets were mentioned in full text. But unfortunately, because unlike software entities, when scholars mention data, especially data sets, they mention data sets in a very inconsistent ways. So the bootstrapping method was not effective in identifying data mentions in full text. So alternatively, we used this content analysis method, which is very popular in social science studies, and scholars have used this method to, for instance, understand how different news outlets portray different candidates in elections. And so, yeah, this work is based on this content analysis method, and I will introduce to the background and the method and the results of data access and use in science. So a little bit about background. So why are we doing this data citation analysis? First is because there's an awareness of the need for more efficient access and more efficient data access and sharing. For instance, as early as 2004, a group of scholars have argued the importance to set up an international framework to promote access to data, and this paper is published in Science, and also in Nature, another esteemed journal. And as you can see here, it says that authors are required to make materials, data, code, and associated protocols promptly available to readers without undue qualifications. And National Science Foundation in the US also accentuated the importance of making data available. For instance, it says that investigators are expected to share with other researchers at no more than incremental costs and within a reasonable time the primary data samples, physical collections, and other supporting materials created or gathered in the course of work under NSF grants. And at the same time, there are a number of standards, indices, and repositories that support data citations. For instance, we have the data site, the Sage site, developed by University of Bath in UK, and there's the renowned Thomson Reuters data citation index, and Dryad. I think it's highly popular among scientists and scholars. Allow them to upload their data at a minimal cost. So this is what scholars and practitioners really want. They want data to be easily accessible. They want standards and indices to measure impact of data. But the reality is that data are more likely to be mentioned in texts than being formally cited. And only 6% of articles cited data as DOI in the article's references. And about 3/4 listed the DOI in the body of the article, and 20% of articles had no citation of data at all. So, which means that scholars do not see data as a formal scientific inquiry, but rather a byproduct of a research project. Because every time we cite an article, definitely we'll cite this article in the reference, but not so much about data, because people think data is just not part of the scientific research. At the same time, I also want to talk a little bit about the psychological part about lack of data citation. First is that scholars usually do not have an incentive to cite the data. For instance, as a junior faculty member, can you hear me?
Yes. Can you hear us?
Okay, good.
Yeah.
Yes. As a junior faculty member, for our annual evaluation, publish a paper that's very good. Secure a grant, that's even better. But I will not really be rewarded or promoted simply because I publish the data or I curate the data. So scholars usually do not have the incentive to do such extra work. So they really see this as an extra work. And second is that there's a lack of standards. So despite all the progress on establishing data citation standards, currently we don't really know how to set it. And like if I have a data I want to share with others, I don't know where to start. And do I upload to my personal website, or do I upload to the institutional archives? So yeah, so there's a lot of policy implications. And also scholars have a concern about if they have the right to share data. For instance, I download some data from Thomas Reuters, and legally, but then if one of the readers requested data, so I don't really know if I can share this data with this reader, because after all, it's Thomas Reuters data, and also in some biomedical research, the things can get even more complicated, as there's certain policies prevented scholars from sharing the data with other scholars. And lastly is that there's a concern over their research being scooped. So I think we are familiar with this concept. Let's say that my plan is to carry out this 3-stage project, and I just finished the first stage, and I published this paper, and also, and then a group of scholars requested the data, and so then I will hesitate in doing so, because what if that by sharing data, this group of scholars will carry on the stage 2 and stage 3 of the project that I have in mind initially. So there's some kind of psychological concerns over data sharing. So with this in mind, this NCDS project, we tend to design a full text compatible method to identify data access and use in a multidisciplinary corpus. We use full text primarily because, as the last slide showed, that many scholars only mention data sets in the text as opposed to formally cited in the references. And second is to understand disciplinary characteristics regarding data access and use. So that's why we need to use a multidisciplinary data set. Lastly is that we aim to review popular approaches for researchers to provide access to data. The data set we used is from +1, +1 articles published in 2014 and 2015. We sampled randomly 50 papers from each discipline, and we have 12 disciplines in total, so we have 600 papers to annotate. So this number may not sound like a large number, but given that the manual work involved to annotate and to read and annotate each paper, we think this data set should be sufficiently large to address the research questions we have in mind. And also many similar articles, they tend to use smaller data sets to annotate, also because the labor involved in this effort. So +1 has a classification scheme, as we can see on the right side of this table. Many of those subjects are quite similar to each other. For instance, there's computer science, and there's also computer and information sciences. So we merged the original 20 subjects into 12 disciplines. So we believe these 12 disciplines can capture the disciplinary features better than the original +1 subjects. And I need to mention that despite the multidisciplinary scope of +1, this journal still has an disproportionately extensive coverage on biomedical research. So even though some articles we see it has social science classification, it's still about biomedical research. So this is one of the limitations of this research. As a future work, we intend to include in our analysis some domain-specific journals, so that the results will be purely about a certain discipline, as opposed to social science and biomedical join some kind of interdisciplinary field. So in our coding book, we have 7 coding items, including use datasets in research, dataset section. So which section did the scholars mention data, and data collection? So if scholars collected this dataset themselves, or if they reuse existing data. Data access means that if the general readers have access to this dataset mentioned in this paper. And data tracking, so if we can track this dataset. And section of the dimension, so where did this dataset mentioned, and type of archives of this dataset. And here we want to make a distinction between data and dataset, because as the results will show to you, you may feel surprised, like by only half of the papers use data. That's not right, because nowadays nearly every publication should have some kind of data, no matter it's qualitative data or quantitative data. So in that case, our this coding will not be quite meaningful, because simply every paper will mention data to a certain extent. So we operationalize the data in the sense of data set. So it has to be a well-defined set of data points. So if you're interested, I can share this article, this operational definition to you. So right now, data and data sets are used interchangeably, but when we talk about data, we are really talking about a data set. So here is an example of how we code the articles. So as I said, we have 7 categories, and you can see one coder just assign a coding item to each article. And then in the end, we aggregate the results of the 600 publications we have. So to begin with, I'd like to share the results with you regarding whether articles used data sets. As we can see, and different disciplines exhibit different characteristics. Medicine and health sciences used data sets in nearly every of its paper, up to 90%, whereas agricultural and engineering, they are less likely to use the data sets in their research. And this slide shows whether articles have a data section. So this is important because it shows how scholars prioritize their research, if it's data intensive or it's mainly also if this article is really about using this data to address a series of questions, or simply that this article casually mentioned where this data set is from, like in the introduction or in the method section. Social sciences and medicine and biology, the majority of their articles tend to have a data section. So either it's like subsection or the section by itself. Whereas at the same time, like ecology and physics, they tend not to mention. Its articles tend not to have a data section. They probably will just mention it in the method section or in the introduction section or in the results section or as a footnote. So there's definitely some disciplinary differences. And in this slide, I show whether authors collected data themselves. As you can see, most of the articles across the 12 disciplines tend to use their own data sets. This is an alarming number, because ideally scholars should tend to reuse the existing data, because for anyone who has collected data and created data in the past, we all know how arduous this process is. So once we spend a lot of effort in doing this, we want others to use our data. But in reality, most authors do collect their own data and for this time, and then next time, if they are working on a new project, we will collect some new data sets to work with instead of reuse existing data, either their own data or existing data by their colleagues and peers. So hopefully that in a few years this number will drop, and scholars tend to reuse existing data more often than it is now. And this slide shows whether articles indicate data collection dates. We think this is an important feature to include in our analysis, because data collection dates are an important indicator to show the relevance of data to a particular research, especially social science research, like for instance, in presidential election, like the survey done by today will be very different from a survey done like a week from now or a week before. So I think that's probably true for every discipline, that it's important to mention specifically when this data set is collected, and so that readers or scholars will have some confidence in interpreting the results, or comparing the results obtained from this paper with other similar papers. So without knowing this data collection dates, then we cannot make meaningful comparisons. And I think some disciplines did a better job than the others, that they tend to mention data collection dates more often, but not so much, for instance, in engineering and biology, that only half of the papers that use the data sets mention data collection dates. And can we access the data sets? And as we can see, most papers across those 12 disciplines provided free access. So this is mainly a +1 situation, because +1 requires and also allows authors to upload a small data set, I think it's within 100 megabytes, to their journals, to their journal as a supplementary material, so that if you have a smaller data set, purely less than 100 megabytes, then I think you are encouraged and a lot of times required by the journal to upload your data set to this journal. So that's why we can see the impact of journal-specific policy to the behavior of data sharing. So that in this case, if they provide access, means that, and if they provide free access, it means that scholars can acquire this data freely and publicly, and potentially replicate the results or doing similar investigations. At the same time, in biology, only half of the papers provided free access, whereas the other half have no access, which is probably not surprising, given that some type of research in biology, some data sets used in biology are proprietary, and so scholars, even though they wanted to share data, but probably their data policy prevented them from doing so. And in certain areas, such as medicine, scholars also leave their contact information, saying that if you're interested, please contact me. So data available upon request is another form of data sharing in those disciplines. So we call this trackability. So if you have we're not quite sure about if it's really a term, but if you have any recommendations, then please let me know. So because I think this is really a made-up word. But I think it's easy to understand is that if we can, so how can we track this data set? So the options are through email without a name, with a name, URL, DOI, and citation. And those categories overlap to some extent, so they are not mutually exclusive. And the most formal way of tracking data set is through URL, DOI, and citation. But unfortunately, as we can see, those two formats practiced in limited number of papers. So majority of them provide a URL. So I think URL is better probably than nothing, right? But at the same time, URL can expire, especially for those uploaded to like Dropbox. Sometimes scholars do that, and then somehow their Dropbox run out of space, and they simply delete some of those data sets, which there's no guarantee that this URL will be always available. In other occasions, scholars upload their data set to their personal servers within the university and provide a URL to that. Maybe in a few years they switch jobs and then this URL is not available. So we cannot really count on URL to track a data set. So DOI is more reliable than URL. But unfortunately, it's not really the case. It's not really the most popular way of mentioning data sets at the present time. And so we're also interested to know the types of data set archives. So the options are personal, general specific, governmental, institutional, and commercial. Again, I think this is more class 1 specific situation in that most disciplines, papers from most of those 12 disciplines, they upload their data sets to class 1. So here is journal specific archive. At the same time, we also say some, like in, for instance, ecology and environmental sciences, where Dryad is very popular in that area because a few very renowned journals have set up agreements with Dryad, so that scholars can share the data, can upload the data to Dryad without cost. So the cost is mitigated by the journals. So that's why we say commercial. So here is non-for-profit company. Probably that's most accurate to describe this category. So you can see the impact of different journals really have an effect on how scholars decide where to upload, where to share this data, and how do they share this data. So as a summary, that we see some disciplinary differences. Medicine and health sciences performed really well in terms of specifying data collection dates, but only half of the articles in chemistry and social sciences indicated data collection dates. And articles in mathematics tended to use publicly available data and employ data citations more often than other disciplines. And in biology and medicine and health sciences, most articles use data sets in research, while only half of data sets are freely accessible. And so in this slide, we'll also show some other disciplinary features. But really, in order to understand, so for instance, why biology and and mathematics use use data citations more often than other disciplines, we need to do some ethnographic research. For instance, to conduct interviews or to observe how scholars really carry out their research to understand these epistemological cultures of those disciplines. So those knowledge cannot be readily grasped from just simply doing a manual coding of full text applications. So that is seen as our next research. So here is an aggregated charts showing like when we aggregate all the 12 disciplines, we could show the general patterns of data access and use in science. And I think the most noticeably is that scholars still, 74% of the time, the scholars still tend to collect their own data sets as opposed to reuse existing data sets. Most of the time, scholars mention data sets in abstract and methods. I think probably because Plus One sometimes have those so-called data journal articles. That's why they probably will mention data in abstract. But other than those two sections, scholars tend not to mention data sets in other sections. Lastly, is that journal-specific archives are the most popular because it's really a Plus One issue. So in the future, we want to include a diverse body of journals to understand scholars across different disciplines, how they access and reuse data sets. And lastly, I want to thank for the generous support of NCDS, and I think without the consortium's support, then this work will not be possible. Thank you.
Thank you, Erjia. Thank you for closing us out. Are there any questions for Erjia? Stan.
I have a naive question. How does a DOI become more trackable than a URL? What is it that's special about it that I don't understand?
GUI, I think is more permanent because, and for instance, I can upload a data set to my web page, and that's a URL. But then I can delete it, or I move to someplace else. Then the university can terminate this, my space in the server. But for DOI, it's usually regulated by a higher organization, either a journal or an institution, or like a data archive such as Dryad, so that there's some sort of guarantee and some kind of certainty there than just a URL.
Well, DOIs are registered, so there are specific registries for that, right? So it's the metadata that makes it more persistent. The metadata, as long as it's updated by...
That makes sense to me, but I don't... I mean, I may be wrong, and I was just trying to figure this out. I'm not a heavy user of DOIs, but I know what they are. And I didn't think I had to give my data to an entity to get a DOI. I could create a DOI for a rock and go drop it out the window, and nobody's going to ever find it again.
But you got to register the DOI.
But you have to register DOI. So for...
Registered, it still can't be found.
Yeah, but you got to have, like for example, OVA manages the registration for UNC's DOIs. So we have a person who curates that and manages that connection for that. And I think RENCI has their own, but someone manages that. And they prevent, they're supposed to keep you from doing that.
Right.
Oh, okay. So it's still, there's no certainty.
It's up to the people managing. Like we tell, when I register a DOI and then put it on the web, I tell the webmaster this URL has to stay the same because it links to that.
Okay, that makes sense. Thank you. I thought maybe there was some special thing where periodically you sweep through all the DOIs and make sure they're still where they're supposed to be or something.
Well, in your system, so for example, Dataverse automatically talks to data site and talks to these people. So it registers the DOI. And anything that changes in the metadata, it automatically changes in the DOI, and everything is linked.
But does it go the other direction where it's saying I'm checking on your metadata?
No, you handle that.
No, you're responsible for handling that, and that's part of the agreement.
Okay, so if you get a persistent identifier, you're expected to persist.
That's correct.
Yeah.
That's correct.
Oh, sorry. Yes, Brian.
I have one quick question.
it's a little counterintuitive to me that the mathematics community cites a lot of data sets. And so, do you have any sense of what kind of articles these math papers are?
I'm sorry, I did not hear your
Sorry,
question.
Erjia, the question was that the fact that the mathematical articles had used so many data sets was a surprise. So any idea on what sort of papers they're submitting or why they would have so many data sets in their papers?
Yes. So I can definitely look into that. But just from a general understanding of this coding process, or from general understanding of class 1, is that this journal is really multidisciplinary and it's very applied. So for any mathematician to submit their papers to class 1, this paper is usually on the more applied side. So it's not like a hardcore mathematics paper talking about different algorithms. So it's more probably about using this certain mathematical algorithm to address a biomedical issue or astrophysics issue. So yeah, so this is more like an artifact because this classification is governed by class 1. So we can only take it for granted. We don't really know what this paper is really about, and maybe a mathematics in class 1 is probably not really a mathematics paper to mathematicians in general. Yeah, so yeah, I can definitely look into that. So that's one of the limitations of using this multidisciplinary journal as our data source.
Thank you. Stan?
So I was really impressed with, I guess it was ecology and environmental science that had 100% compliance. What is it about that community that would yield such laudable results?
Part of it's that dryad that he mentioned.
It's just become kind of universally accepted. That's where you put your data.
Yeah, and it's free and
For evolutionary biology to start with, so that becomes a lot of the core, the journals they talked to originally to start partnerships.
Yeah.
Ashok?
I was going to say that we have been doing some similar analysis on publications related to environmental health sciences. And what we found is that the availability and or pointing to data availability is very much dependent on the publication. That some publications make it an important part of getting a paper out there, and then the level of specificity as to where you can find the data and how you can find it goes way up on those papers. And in others, it's the largest that we found, the largest case that we found was send us an email, and we'll tell you if we can get the data.
Okay, Erjia, thank you so much for your time and for the great presentation. We really appreciate it.
Thank you.